هعملها مجانا بس في الاول بس عشان كله والهدف منها ولهذه المجانيه احنا في المركز ده عشان ليس فلوس خالص. هي المركز ده عشان ينشر الثقافه نعمل نحل بيها مشاكل وده هدفنا الاسمى. مش هيشتغل المركز الا يعني لغايه دلوقتي كل الناس المرتبطه بهذا المركز هم 3 4. طبعا ده كلام مش مظبوط خاصه ان هم تخصصات مع النانو تكنولوجي بطبيعتها لازم يبقى كل التخصصات شغاله مع بعض. يعني الطب، الصيدله، العلوم كله يبقى بيت المركز. الناس اللي هم الى الان مرتبطين بمركز النانو وبيحاولوا يشتغلوا معاه كلهم هندسه فقط. عددهم 3 4. انا عايز يبقوا 300 مش بهزر. ده مركز كده في الجامعه ده مش رقم مزيف لا هو فاهم كده. انا عايز يبقى فيه لو كل كليه فيها 10 ده حاجه ده رقم متواضع كويس. فانا نفسي اولا هنعمل بطاقه التعارف ديت عشان مش هسيبها كويس. هنعتبر ان كنتوا اشتراك الدوره بتاعكم الفلوس هتدفعوها لنا مش هناخد منكم فلوس. لا هتدفعوها لنا ان كنتوا نمره واحد هتعملوا ابحاث معانا. انا مش يعني نمره 2 هتكونوا فرق بحثيه معاكم يعني اذا كان في معاكم معيدين اذا كان في معاكم زملاء اذا كان اي حاجه يعني عايز الواحد يجيب 10 لو سمحت كويس. فهو الجهاز بتاع النهارده بقى طبعا انا قلت فلوس مايكروسكوب لازم يبقى عارفين. انا مش هتكلم يعني هسيبهم كده بس عايز اقول حاجه. الجامعه فيها النهارده سكاننج الكترون مايكروسكوب وترانسميشن الكترون مايكروسكوب في المركز اللي هو في الزراعه. وبيننا وبينهم اتفاق ان احنا لو هنستخدم جهازهم او هم هيستخدموا الاجهزه بتاعتنا هتبقى يعني اوبر مخفضه يعني عشان الاتفاق ده كله مصلحه الجامعه في الاخر كويس. نظام الفورس مايكروسكوب دوت اللي احنا جبناه مميز جدا وحديث وفيه امكانيات يعني جباره بنسبه كبيره قوي. قد ما نحتاجش على الاقل مش هنحتاج الاساسيات ويمكن ما نحتاجش كتير هم هيشرحوا لنا بقى. بالاضافه لامكانيات القياس العاليه جدا في امكانيه تصنيع ولو محدود. يعني احنا مش بس بنقيس يعني الالكترون مايكروسكوب بنقيس بس لا في حاجه اسمها ليثوغرافي هو هيشرحها لنا برضه. في ليثوغرافي دي تقدر تخلينا ان احنا نعمل بروسيسنج سكراتشنج او ديبوزيشن او اوكسيديشن وتقريبا كده على كل يعني بينزل مسافه ابعاد صغيره كلها حاجات انا بقول حاجه مش صح اقول دلوقتي.
لا okay it's not. So what I think now is like first just presentation about half an hour about let's say different application of atomic force microscope, what kind of information you can get from atomic force microscope, and then after that we go in detail with the scanning and with the system. So I mean, so now I'll make like introduction regarding the application in let's say in research and industry, and then maybe you can have idea in your mind and things like that. Do you see the screen or should we the light a little bit? Okay. Okay. So this first, so I am coming from NanoSurf. So NanoSurf is a company based in Switzerland. We have here the headquarters. We have office in USA. You have office in Frankfurt and office in China, and we have also the only company who has an AFM on Mars, so outside of Earth. So I mean, this is, let's say, different products. So what we have now today, we have this last controller we have, and this scan head, and this is the isolation table. So this is the system you have today here, okay? Because we have different system for education, for research, for industrial, and now this is the research system for you. So how it works, scanning probe microscope. Actually, what do you do usually? You are scanning the surface line by line. So mean, let's say, you scan the surface point by point, and it's a probe because you are, let's say, local, and it's called microscopy because we are, like, say, at nanoscale or microscales, and that's why they call scanning probe microscope. So the AFM is one of this family. So maybe it can be, say, let's say, scanning force microscope, which means atomic force microscope, and they say, for example, you have scanning tunneling microscope, and you have, let's say, scanning electronic microscope, and all this family. So this is all called, let's say, scanning probe microscope. So everything is using a probe that is scanning the surface. This is known as scanning probe microscope. And then this probe, it can be, let's say, electrical, can be magnetic, can be any kind of interaction, and then you can measure the interaction between this tip and the surface, let's say. Okay? So how it works is the scanning probe microscope. So we have here, let's say, a sensor, and then here you have, let's say, a tip to scan the surface. And then we assume that this tip ends with an atom. And then you measure the interaction between the tip here and the sample. And then this interaction is controlled by a feedback here. So you have feedback to control this interaction. For example, let's say if the interaction is just a force, then you control the force between the tip and the sample to keep it, for example, constant. Okay? And then you have a feedback to control it with actuator, and then everything is drawing on a computer. And then everything is drawn line by line on the computer. Okay? So what kind of interaction we can measure? We can measure force. The force we note as normal. And then we move at the same time. So we measure the force, and then we scan the surface, and then we can get information about topography. And usually with AFM we can get, let's say, 3D topography of the surface. And if you measure, let's say, kind of, let's say, tunneling current, actually this is in quantum effect in physics. So you apply voltage between tip and sample, and when you are very close to the surface, that's about 5 nanometer maybe, then there is a tunneling current between tip and sample. And then you can also measure this current. This is called scanning tunneling microscope. If you measure, let's say, a magnetic force, so what you have now, you have magnetic interaction between tip and sample, then you can measure, let's say, the magnetic structure of the surface. And again, if you make, let's say, you apply voltage between tip sample, and then you can measure, let's say, the electrostatic charge of the surface. And this may give you, like, say, charge distribution. I mean, for this we use what we call the special mode is called phase, and this will come later in my training about this. And then if you measure the interaction, let's say, at the same time we can measure different information at once. For example, we measure the force, and then we measure the phase. That will give us information about material contrast. For example, if you have, let's say, two different material on the surface, the interaction between tip and the material is different. And this is give you different contrast on the surface. This is what we call, let's say, phase contrast. I mean, if you measure also, if you measure also the force and then the current, so you apply voltage between tip and sample, and then you scan, and then you measure the current, what you get, conductivity map of the surface. And last information, let's say, the most important, let's say you measure the force, and then you apply, let's say, external modulation to the voltage, let's say AC volt to the tip, then you make small modulation of the voltage, and then you can get what we call, let's say, work function, or let's say how much you need, let's say, electron, let's say, or voltage to remove an electron from surface. And this, for example, they use it in solar cell. For example, they want to measure the surface potential and how many volts you need or to remove electron from surface, for example. So the information we get is like topography, which means 3D image. So we can measure, let's say, roughness, step height, structure size. And for this, we use what we call contact mode and dynamic mode. There is different mode of measure, and then I will come later to explain these modes. Then we have here what we call phase contrast for these three, and then here we can measure different information depending on the tip. How it's, let's say, if it's magnetic tip, if it's electrical tip, then we can get different information on the surface. And also, we have, let's say, we can measure also conductivity on the surface. We use, let's say, also contact mode, and we'll come later also to explain. We can also measure friction on the surface, work function, as I said. We can do also stiffness, which means spectroscopy, and we can do also nanolithography with AFM. Yeah. I mean, what do you have in your system? You have all this except this one, except the work function. And I mean, here stiffness, you have the basics. You can also buy the advanced models. You have, but this is, I mean, in general, you have almost 90% of the application. Okay. So how it scans? So you have here a piezo. This piezo is moved on 3 direction, X, Y, Z. And then you have the tip here. This is the cantilever here. This is we call cantilever. And then you have the tip on the lower side of the cantilever. And then you have a laser on the back side is to control, let's say, the feedback when this is moved up and down the deflection. And then what's happened? So you scan the surface line by line. So when you are scanning here the surface line by line, it can go up and down. And then it's drawing on the computer line by line here. And then here you have the line, the real-time scanning. Okay. And then actually what is can happen, you see on the image, you will see, let's say, different color. And this different color means different height. So for example, let's say, usually dark mean lower height and the bright mean higher height. Let's say it's black and white, so mean black is lower and white is higher in height. And then if you look to the image, you see, this is, let's say, lower than this one in height. And then you measure it like that. So first application is, let's say, you say contact mode. So what do you have here? So I will explain a little bit what is contact mode. You have here, this is, let's say, the cantilever. This is we call cantilever, and this is the tip is here. You have laser coming to the cantilever and going to the detector. Okay? And then what's happened in case we are wanting to scan something on the surface, let's say, assuming we have particles. And then if you see this is a particle, this you have the laser and the detector. And then when you, and then when the particle, let's say, come to the surface, to the cantilever, when she's scanning, it has, let's say, something. It will bend. Okay? When the cantilever is bending, the laser is not on the detector anymore. Let's say, we say, let's say this is, let's say, initial position of the laser. Okay? And then when it's bending, or let's say here, let's say this is the initial position in the center, and then it's bending, it's moving up and down. And then when this part moving up and down, this part here will move also up and down in order to keep the laser in the center. Okay? So for example, the laser is in the center, then the cantilever will make up or bending a little bit. Then the laser is not anymore in the center. It will move up or down. And when the laser is moved up and down, the piezo, which is here, this part, connected to this part, will move up and down in order to keep the laser again in the center. And this is how we measure, let's say, the height. I mean, this is automatic. This is the AFM. It works automatic. So just how the AFM works. Okay? Like, is it clear or? This is continuous. I mean, it's all the time. I mean, so maybe this is a small video. Will explain a little bit how really the AFM work. So I mean, now just we remove, let's say, the plastic part or the housing of the AFM. So first of all, you have, let's say, motors to approach the tip to the surface. And this motor is on the backside somewhere. So you can apply, by applying voltage, you can move up and down the scanner, okay, to be close to the surface. And then this is just the motor, so we move up and down. And then via software. I mean, you have manual, and when it makes the final things, you make automatization. So you have all options, manual, automatic, and so if you see first, so we have here, let's say this is coil, but when you apply voltage, this is moved in one direction, okay? And then when you apply voltage in this direction, that will move also in X direction and then Y direction, okay? So by applying voltage, and that is moves the scanner in one or other direction. And also in Y direction. And then when we are scanning the surface, so all three work at the same time. They move in one direction or another direction. But of course, it will move very slow, okay? And then you see the applying a little bit voltage in one direction, move this direction, and then in Y direction, and then you get your image. Then this is how you scan the surface. Now if you go now to the tip, as I mentioned, so here we have the laser and the detector, and this is the tip here, okay? So you have the laser is coming to the cantilever here, reflected to the detector. Now let's say we want to scan a surface. So let's say we have, let's see here, some height difference, some structure on the surface. So now we in touch in the surface, we are moving. Then we have let's something. The cantilever will bend up. If you see, the laser was not in the center, then the piezo move up or down. Now it will go down. The laser will move down. Then the piezo will move up to keep the laser again in the center. And this is how really moved in that direction. That's why it is important to have the laser on the right position to control the piezo feedback. And I mean, if you have nothing, then you will destroy the cantilever and it destroys the surface. Okay? So I will show now maybe some example about, let's say we start with different contact mode, dynamic mode, and then we show all until the end. So for example, with AFM, you can work on non-conductive sample, let's say like ceramic or any kind of sample. You can also measure in liquid media. It's not like SEM, whether you have to make, let's say, some coating on the surface. So it can work on conductive and non-conductive sample, the AFM. So here an example of ceramic, for example. This is, let's say, as fired, and then you can see the surface actually is rough, is not really clear. And if you measure just the height here, you see this is like 3 micron height. And then what we do, let's say we make some polishing the surface to make it smooth. And then you make another image here, you see that is more flat, let's say the surface, smooth. And then you see that the height is about, let's say, 900 nanometer. So let's say you can make, let's say, sample preparation, polishing something, and then you want to control the surface quality of the sample. You need to have some gold coating or something, but with AFM you don't do any kind of coating. No need. No need with AFM. Okay? And for example, this is another example of cosmetic industry. We have USA, it was a USA company. They want to deposit something on hair, let's say color hair, and they want to see what's happened really on the hair at the surface level. So this is an image of hair, one hair. So we measure this. This is an image of 40 micron. And then if you look at the micro scale, you can see there is, let's say, this is, let's say, like terraces or let's say steps between on the surface. And then when we deposit, let's say, something on the surface, you see there is some particles or nano-reflector on top of the hair. And this is, for example, let's say, gives the shiny color of hair. Let's say when ladies change colors. So there is actually some nano-reflector or nanoparticles on the surface. And this gives a shiny color, so something stick on the surface. And then, of course, you can measure this, and then you can measure the size or diameter of these nanoparticles. So that was at the beginning. Now, let's say contact mode, what I call it contact mode. So that means you have the laser, and then you measure the deflection of the laser, and then the piezo move up and down. And there is now another mode, we call it, let's say, dynamic mode, or tapping mode, they call it. In this case, what's happened? So instead of so that the cantilever was fixed, let's say static. In the second mode, so the cantilever will make oscillation. Okay? So now the cantilever makes oscillation. We have, let's say, the piezo, and we can make, let's say, vibration on the piezo, and then the cantilever can move up and down. Okay? And then here, what we measure, instead of measuring the deflection, we measure the amplitude here. So we measure from here to here. We can measure the amplitude, and then we can measure also the frequency and the amplitude of the oscillation. Okay? So how it works? So we have here, let's say, if we take, usually we take what we call resonance peak. So we have like maximum, and then you can measure the amplitude of this maximum. And here you have, let's say, the free vibration amplitude, and here we have what we call it, let's say the real set point. I mean, I will explain it when I really start measuring with the system to explain you better. This is very complicated. So what is important is that you know that is making oscillation now on the tip, and we measure the amplitude, and we try to work, let's say, at constant amplitude. Okay? So we say the amplitude is constant. So with this first mode, we're saying, okay, keep the force constant between tip and sample, And with this mode, now we say keep the amplitude constant between tip and sample. Okay? So, and usually this mode is used, let's say, for soft material, let's say DNA, nanoparticles, any kind of surface. While the contact mode is mainly used, let's say, for hard material. Let's say when you have something solid in the surface, is very solid, then we can use contact mode. And when you go to, let's say, polymers, soft material molecules, then you use this mode because you want to reduce the interaction between the tip and the sample, and for that you use, let's say, what we call dynamic mode. Okay. So this is an example of, let's say, artificial DNA on mica. We have here, let's say, one molecules, let's say, the same. And then when you connect this molecule together, they are, let's say, randomly like that. And then when you put salt inside the solution, then let's say the molecule is oriented. Okay? And these things, and then you can make, let's say, long chain of DNA or polymerize the surface. And for example, so if you look here, so this is, we have here, let's say, fresh sample of DNA, and you can see this is the molecules on the surface. And then what you do, we just leave it for, let's say, 1 month, and then you look what's happened after a few times. And then you look here after 1 month here, you see that you have all polymers, or let's say all molecules are connected together and making, like, say, a film on the surface. And then you see here the polymers, and then you can measure these polymers here on the surface. You can see that it's organized. And then, yes, so you can make like line here, and then you can measure the size of these polymers, how big they are. And then if you make like line profile here, this one here, you just cut it, and then you can get something like that. And then you can measure the height from here to here, and then you see it's about, let's say, 7 angstrom. So you can see this is about the height of the molecule, which is 7 angstrom. Okay? 0.7 nanometers.
Sorry, the previous one, a little bit more. You mean the growth of the polymer, we can follow the growth steps by...
I mean, here, let's say this, yes, but I mean, it depends how fast is this growth process. I mean, here is long process. It took, let's say, 1 month to get this from this to this. I mean, you can, for example, what they do usually, let's say, make image today, they make maybe image tomorrow, the day after, and then see after a few days what happened in real time. I mean, if you do, for example, what you do usually, let's say you want to deposit polymers, maybe you can deposit a little bit, then you can scan, maybe half monolayer, for example, 1 monolayer, 2, 3, 4, and then you can see how this is changed the surface. And then you may try to understand what's going really on the surface.
Small piece of DNA on the surface.
Okay.
This has a special number. You can call this number.
What do you mean?
Maybe
I mean, what usually you can do, you try to scan the surface, let's say, before or after deposit something. And then you see what's happened, what's it changed. And then you try to understand really the surface morphology. Okay. Mm-hmm.
we can follow the interaction with this membrane and small pieces of DNA.
You can follow the morphology as a function of time, yeah. But I mean, I think the interaction, because the interaction usually is very fast. I mean, this interaction, you cannot see it. If it takes few seconds or less than few seconds, this is quite fast. Yeah. I mean, here we are taking, let's say, 1 image, it takes like 5 minutes. Okay? So just to have an idea how it's fast the interaction compared. Yes. So you need 1 image is like, it's 5 minutes. Yeah, interaction is, when you say you deposit something, the interaction is already done before you start scanning. And then you see the surface when, yeah, let's say 4 or 5 minutes. And the interaction usually is quite milliseconds sometimes.
Okay. So during the interaction, you cannot follow any changes. But you can
After the interaction, you see.
You can make a second scanning after.
You can change parameter to see how something.
After a day, or after what you want.
or let's say you change, let's say the concentration, for example. Let's say you deposit something, you have concentration X, and then you see the topography. Then next time what you do, okay, you maybe increase the concentration or reduce the intercon concentration, and then you see what's happened again, the result. That you can see it like that. Okay. So another example, for example, here we have like say the CDs. So here, let's say you can see this is the bit of the CDs, and then what you can do, for example, from time to time, industrial, they want to measure, let's say, the size of the CD, how many, let's say, megabyte or gigabyte on the surface. And what they do, let's say, an image like that, let's say 20 micron, and then they can evaluate the number of bit, and then they calculate, let's say, the number of bit by, let's say, micrometer size, and then they can, okay, say, okay, this is the size of my bit. Or, for example, this is another example of grid, let's say, photoresin interference grid, and then they want sometime to see if this grid are, let's say, straight, or this is, let's say, have defect on the surface, or some information on the surface. So another example, for example, is about high resolution image. So we have, let's say, micelles. This is, let's say, application in pharmaceutical. We have particles. We deposit solution. We deposit them on the surface, and then we let's say dry, and then we scan the surface and the particle to see the particles. And this is, let's say, topography image of the micelles, and this is, let's say, 3D image of the surface. I mean, you can see this is the particles on the surface. And let's say another example of, let's say, quantum dot. So we have, let's say, particles. I mean, quantum dot is like acting as a single electron, and you deposit, let's say, this is solution of nanoparticles, and you deposit them on a surface. So you can see here, actually, if you look here on the background here, you see there is steps here, and actually this is like the atomic steps. So this is about 3 angstrom height, and then you have the particles on top of this, and then you can measure the size of these particles to see how big they are. Okay. Or, for example, in some case, you can get really atomic resolution on the surface. So you can see atoms. So this is an example of, let's say, mica here, and then this is from here to here is about maybe 3 angstrom high. So you can see the atoms on the surface. But this is something very difficult to get. This took like 5 days to get this image. And this one I will not talk about. So no, I mean, you will see, I mean, maybe you will destroy that tip, and then you have to change it.
No warning?
No, no warning, no. I mean, there is one, you have just, I mean, there is just parameter you have to follow, and that's fine. I mean, you will, with experience, you know what exactly how to do. So, you mean you have just to change the voltage, and I mean, you cannot destroy it, I mean. Okay? So, another example, let's say here about bacterial rhodopsin. I mean, this is, let's say, molecules on the surface. It's organized like as a trimer. So you have, let's say, I mean, this is kind of molecules, and then here you have, let's say, 1, 2, 3 maximum. This is the molecule. And then you can put it on a surface, and then you can scan it, see how it's organized on the surface. So once we took, let's say, we use also mica surface, and we deposit this bacterial rhodopsin on the surface. And then if you look here, we have here, let's say, this is a small, let's say, island of bacteria together, and this is another one here. And then if you see, if you made, let's say, a line here, you see that the height between here and here is not the same. I mean, this is due to the electrostatic interaction is known on the literature. Okay? It's not the more important point for me. Then if you will go to this cluster, and then you measure inside this cluster, so you can zoom inside, and then you make another image, and then you can see here this self-assembling of this bacterial rhodopsin on the surface. So you see they are organized on the surface, and then you try to understand, if you make, let's say, autocorrelation image, you can see there is 1, 2, 3, which is the 3 trimers of the molecule, so you can see them. Okay? I skipped this, I didn't, I move it. It's not important. And then you can put like this, and then you can see, let's say, the bacterial rhodopsin or the molecules on the surface. So if you want to scan the molecules at nano, or let's say nanoscales. Another application maybe is also interesting for you is about, let's say, electrochemistry. For example, we have here an example where we can, let's say, follow up the growth process in real time. We make electrochemical application, depositing on the surface, and follow the growth process on the surface. So for that, let's say, you have the microscope, and here we have, let's say, an electrochemical cell, and this electrochemical cell is connected to potentiostat. Here you are applying to potentiostat. And then when you apply voltage, so either you can deposit something on the surface or remove something from the surface. You apply depending on the polarity. So this is an example of, let's say, copper deposit on gold one surface. I mean, if you look here, I mean, it's not really clear, but we start here, let's say, depositing. We deposit at, let's say, minus 50 millivolt. I mean, there is this small point here. So that means we are really starting deposit. So we deposit and we scan at the same time. Of course, the deposition process is very slow. Otherwise, we cannot. And then what we do here, we continue depositing on the surface. And then you can see, let's say, the growth starts at minus 10 millivolt. And then you can see we are making the growth. And this, let's say, understand what's happening on the surface. And if you look here, we have, let's say, what we call 3D growth process. Let's say we are making a island, a 3D island, triangular island on the surface. I mean, the reason is the surface is oriented 1, 1, 1, and then it's make it like triangular growth. And then you say, okay, I have a growth, triangular growth on the surface. And then after that, you want to understand at which, let's say, voltage you can dissolve the surface. And then the solution here is start at, let's say, plus 50 millivolt. So then you can, let's say, follow in real time what's happened on the surface. I mean, maybe you can have also different kind of growth on the surface, maybe 2D growth or something else, so you can try to understand the growth process at the very beginning of the deposition. I mean, another example for industrial, let's say, application, we have here, let's say, pens. So the pen we use usually, you have a pin balls at the end of these pens. And usually this has to be within a specific range of roughness. If the surface is too rough, when you want to scan, let's say, maybe liquid will leak from it. And if it's too smooth, when you want to write something, maybe it will scratch the surface and maybe you cannot. So it has to be within a specific range of roughness. And at the beginning, what they do, I mean, let's say they cut some tungsten, I think, and then they make some milling, and then to measure. And then one expert, let's say, they try and then they write something and say, okay, this is good, not good. But sometimes if you want to have an exact and precise value of these balls, I mean, what they do, so we measure the roughness of the surface. I mean, here we have, let's say, special holders. Let's say here you can put, let's say, small balls inside. I mean, usually they produce, let's say, 20 million balls per day. I mean, let's say they measure usually, let's say, 50, 100 balls. That's from over 20 million. You put the balls, and then the AFM comes and then scan all these balls automatically, make automatic measurement, and then you can get, let's say, the value of the roughness. I mean, if you look here, let's say the roughness here is about 0.091 nanometer. This is good. And when you are going to 0.1 nanometer, let's say, this is micron, sorry. So when it's 90 nanometer is okay, and then it's like 100 nanometer is not okay. So it's very precise. And then it gives you, let's say, this is made automatic. So usually they don't need to care about it because this is not research, this is industrial. They just press the button, give everything, and they say, okay, or not okay. So this is an example, let's say, of tungsten copperid spheric, where you can see the roughness is about 2 nanometer. And this is another one, ceramic sphere, where the roughness is about 8 nanometers. I mean, if you look even on topography from here to here, you can see this is rough than this one because this is flat, it's clear, okay? So this is, let's say, topography image. In addition to topography, we can do what we call phase contrast. And how it works, the phase contrast. So it's easy. What we do, we have measured here, we were measuring just the amplitude, constant amplitude. In the phase, what we do, we compare the excitation and the detection, and we see whether there is a phase shift between both. I mean, you study in the school or when you have, let's say, oscilloscope, and then you measure, you have two signals, and then you measure the phase shift between these two signals. This is exactly the same thing. We just measure the phase shift between these two signals and compare the excitation, how it looks. So for example, this is an example of polymers. We have, let's say, PS and PMMA polymers, so polystyrene and polymetacryl copolymers. If you look, if you put two polymers on the surface, if you make topography image here, you cannot see, let's say, if you look to this area here or this area, you cannot see, okay, this is what and this is what. It's not clear. And when you make phase contrast, this is made at the same time here. You can clearly see this is one polymer and the green one is another polymer. We can really make a difference contrast between both polymers. Okay? Or this is another example of PS and PB copolymers. When you do here topography image, you see this is, let's say, this one and this one. Actually, you know that is two different polymers on the surface. And you want to see whether these polymers, let's say, make a new phase or they are, let's say, separate on the surface. When you do topography image, here, you see this is, and this has the same contrast. You cannot say which one is one and which one. When you do a phase contrast image, is it clear this one has a different contrast than this one here, which means this one is different than this one. I mean, you have like two different material, you can make different contrasts. With AFM, you cannot say this is let's say PS and this is PMMA. You cannot say. You can say just this is one different than this one. And then with experience, you know that is this is PS, this is PMM, PB or something. So then you know it from different measurement. You can then understand it. The scale is here 30 micron. 30 micron. Okay. I mean, the resolution of the system is sub-nanometer. Yeah. But you can go, let's say, you can make image up to 100 micron and goes down up to 0. Okay? So this is the scale you can use with the microscope. So another, let's say, example about using the same phase, but this now is magnetic structure. So we want to get, let's say, magnetic information on the surface. So in that case, what we do, let's say you have here a surface, which is magnet, and then you have a tip, which has also magnet. Okay? And then you just scan at constant height. So that means the tip is not touching the surface, but at constant height above the surface, let's say 100 nanometer above the surface. And then you measure the magnetic interaction between tip and surface. And let's say if the tip is scanning, let's say, in this direction, and here you see, so the spin is in this direction here, and the spin is in this direction down, and then it's perpendicular. So there is no interaction between these two. Then there is no, let's say, phase shift. And this will give you, let's say, this one. Okay? Here. Then when we arrive, let's say, at this position here, so here we have, let's say, the spin is up, here the spin is down, we have, let's, attractive interaction. When you have attractive interaction, mean you shift by higher frequency, because let's say the tip is going down and then it's attractive. Then you, let's say, you increase the force to make it, or increase the speed. Then it's going faster down. When it's going faster more, that means the frequency is increasing. Okay? And then this frequency is going to higher frequency. When you go to, let's say, to this position here, you have, let's say, repulsive position. And so you have, like, and then what's happened when it go down, it have like some repulsive, and then it reduces the frequency. And then the frequency is going to lower position. Okay? And actually what's happened, so you have here, you have this is 0, then it go either up or down. And then just you measure this variation, how it's going up and down, and then you measure this with the AFM. So this is an example of hard disk. So this is the hard disk, you know. I mean, if you look to the topography image here, you see just, let's say, some lines, scratches, nothing special. And when you do a magnetic image on the surface, so you can see this is the magnetic image of the hard disk, and then you can see here there is this is the magnetic domain here, and this is the black one as another magnetic domain. Here is just simply, let's say, the interaction is attractive between tip and sample, and maybe here is repulsive between tip and sample. So this is the domain. And when there is no interaction, like here, you can see in between here. So here, you see that here there is no magnetic information. Exactly. So then you can see all of them on the same image. So if you have magnetic or no magnetic domain, so you can find them on the surface. Is it clear? So another, let's say,
Going just want to take 1 minute to control if the voice is so quiet. Yeah. Okay, I'm sorry.
okay. And now, let's say what we can do also, conductivity on the surface. To do that, what you do, usually you just apply voltage between tip and sample, and then you measure the current on the surface. And let's say this is an example of some kind of transistor. Actually, there is lines here on the surface, and then you want to measure to see whether this conductive line, there are no defect or there is defect on it. Yeah. So when you do, let's say, conductive image, usually this being here has higher conductivity current than this one. And then if you look to this line here, you see at the end here you have, let's say, less conductive current. And that's the idea to want to see whether this line are all conductive or not. This is was the idea. Okay? I mean, another example, let's say, is about friction, or what we call also lateral force. So how it works, this one, when you are scanning the surface now, so at the beginning we have, let's say, the tip or the cantilever go up and down when we are measuring in topography, contact, or oscillation. Now what's happened when we are scanning, if you have some time of friction, the cantilever can make bending like that or like that. And when you are scanning, if you have some friction, the cantilever may do like this, or maybe they do like that. Okay? And this is we call lateral force, or make friction. And then here you see the detector is going in this direction, not in that direction. So at the beginning we always working in this direction, and now we can measure the detector in the other direction. So this is an example, let's say, of nano ink deposit on gold nanoparticles. If you make topography image here, you see it is not really easy. If we forget completely about this image, if you look just to this image, we cannot see really where is the ink on the surface. We cannot say. But when we do really the lateral force, we can see here we have different friction, different contrast because of the ink is on really deposit here on the surface. And then if you have, let's say, different friction on the surface, different material, you can also get information about that. No, here is not topography. This is friction. So it means, let's say, has the dark one has different friction than the surround. Okay. So this the color. Yeah, but here, this is. Let's say, if you look to this image here, this is the height. So this is nanometer. Okay. And this is, let's say, 4.22, 432 here, and then here down is 421 nanometer, okay? So that means from here to here you have like about 10 nanometer height, okay? If you look to this one here, this is in volt, okay? This is in volt here, let's say. And then the lowest point is 0.94 volt, and the highest point is 1.17 volt, okay? Here, if voltage means, also, if you have dark voltage, maybe you have, let's say, higher friction, or if you have, let's say, bright, you have a lower friction. Okay? This is here the meaning of that. In topography, dark mean lower, and bright mean higher. In another mode, let's say, special mode, let's say this one, this is different friction, not different height. Because now we are measuring friction, we are not measuring topography. Okay? Let's say, to detect different materials, this is, let's say, different friction. Or also, for example, if we go here, so here is height. You see, this is, let's say, minus 80 nanometer to plus, let's say, 40 nanometer. Okay, this is none. While here is in degrees. So this is, let's say, minus 80 degrees up to 20 degrees. So this is not height. This is different contrast. Okay, just in topography, this is different height. This is different contrast material. The other one is different voltage, which means also different friction. Okay. Okay. Another application is about, let's say, work function. So in that, you usually actually apply, we will not go fast in this one. We just apply an external voltage. So you have, let's say, tip making oscillation, and then you add an additional voltage to the tip. Okay. And this is an example here of, let's say, this is an isolated surface topography image here. And then what we did, we just applied, let's say, charge. We deposit some charge on the surface. And when you have like isolated surface, then the charge will stay, cannot go anywhere. Okay? And then you do Kelvin probe images on the surface, or let's say surface potential, and then you can see here, you have, let's say, different voltage. I mean here, bright means higher voltage than the dark one, okay? And then this means this actually is the charge we deposit on the surface. And this two image is made at the same time. So this is the topography, and this is as a charge image on the surface. Okay? Another example, let's say, is about stiffness. So with AFM, I mean, up to now, I was just showing topography image, all image. I mean, what we can do also, we can do spectroscopy with AFM. For example, what we do now, instead of just scanning the surface, now we just go up and down. We go up, we touch the surface, and then we go up again, and then see what's happened. So if you look here, this is the, let's say, means there is different kind of spectroscopy. You can make like force as a function of distance. So you measure just the force, how it changes as a function of distance. You can measure IV curve, let's say how is voltage change as a function of current, amplitude, other things. The most important one is the force as a function of movement. So what's happened? If you look here, so they have that position A, which is mean the tip here is far from the surface, about few nanometer, I don't know. So and then what we do, we go down. And we are going down, 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 until we are very close to the surface. When we are very, very close to the surface, there is attractive interaction between tip and sample. Then the tip will go very, let's say, to touch the surface, which is position B. Let's say it go very sharp. And then what's happened in position C, we are still going down, so we are pressing inside the material. And when we are pressing, then the cantilever makes some bending. It can go like that, okay? And when it's making some bending, we can measure it. And then this is, let's say, C position, okay? Then what we do, we go up again. We will not continue going down. We broke the cantilever. We go up again. When we are going up now, so we are going up, we will not stop at this position here, exactly. No, because what's happened, so when we are going up, there is, let's say, adhesion force between tip and sample. And then, so what's happened, you need more force to move it up. And that's why the tip usually is go further down, and at certain point, it will go up immediately, because then, and then will go up, okay? And then this is the F position. And then you can see it here, E and then F, okay? So from this here spectra, we can get two information. One information is the stiffness, and the stiffness is measured by measuring the slope here. I mean, because each material can give you different slope, and then you can measure this different slope. And the E position here, it gives you the adhesion force between tip and material. So if you have different material, this maybe can be higher, lower, it depends on the material. And this slope maybe can go lower, higher, depends on the material. So you can get like stiffness and, or let's say elasticity and adhesion information from this curve, okay? An example about that is, let's say, the nanomechanical signature of breast cancer. So they use the AFM to detect the breast cancer, real breast cancer. So what they do, you have, let's say, biopsy, they make a needle, they take, let's say, a sample of 1 centimeter times 2 millimeters. Then you come with the AFM, and then you measure, let's say, just make spectroscopy at different places, and then you measure the stiffness. So if you look inside the cell, so you have here the cell A, then you press inside it, which is like, say, soft material, and then you get here different slope, okay? And then you try to compare the slope together to see what's going on, okay? So this is an example here. I hope it will work. Okay. Yeah, come on. Yeah. So let's say here's just show you how to make like sample preparation. I mean, this is something really specific, but just to show you what is can be possible. You have this is, let's say, the needle, and or let's say the sample that we want to measure. We fix it in some buffer solution. So first it has to be alive, otherwise if it died, you cannot mean less. I mean, for AFM, I mean, if you want to measure, let's say, cancer, then you put everything in solution, and then you put it under the AFM, and then you put the AFM, and you put the acoustic enclosure, you close it because you won't be very sensitive to noise. And then you go to the image here. This is the sample you choose, let's say, different place on different position. You ask, okay, make me topography, or let's say the image size 70 micron. I want to do stiffness measurement on the surface, and then you ask him to go. And what's happened? So you have different spectra, and then down you have, let's say, the histogram. And on the left side, you see that you have different pixel. I mean, each pixel means one spectra. And then when you make the spectra, it calculates immediately, let's say, the stiffness and the adhesion force. And then you can get, let's say, histogram out. When the image is done, you can get histogram of stiffness or adhesion force. And just you make comparison between healthy cell and let's say, non-healthy cell. And then you see, okay, what's going on, what's changed, okay? Then you have, let's say, different image, different place. When it's done, then, okay, you go to make a study to understand what's happened. So this is the case of, I mean, this is histogram, this is not height. I mean, this is like statistic. Usually, let's say, sometimes you get stiffness 1 Newton per meter, maybe sometimes you get 1.1 and something like that. And then that means you have distribution of the stiffness. And then you make a height, let's say, histogram out of this. I mean, to see what is, how is the distribution on the surface. Okay? And then if you have, let's say, here normal tissue, and then you look here that you have, let's say, we can say you have like uniform peak, one peak. When you have, let's say, benign, you can see if you compare this to this, so you have, let's say, it is wider, and I mean, let's say, if you want to fit this, you can fit it in let's say, two spectra, okay? And when you have, let's say, invasive cancer here, is it clear if you compare this one to this one? Here you have one peak here, and then you have another one here, okay? So, I mean, this is the stiffness map. Yeah, it's just map. No, you cannot measure concentration. You can measure just mechanical properties. Just interaction between tip and any kind of material, but not concentration. It's not chemical. It's not chemical information. Yeah. Okay. And then if you make a comparison, so you say the frequency of stiffness. This is the healthy cell, and this is, let's say, the cancer tissue. And actually, if you have this peak is higher, means the cancer is more aggressive. What's happened here? Actually, you have here, let's say, the material in this side here is more soft. I mean, if you have two, cancer, usually the cell is divided into two. And that means that the tissue of the cell is very soft because it can be divided into two. And if you have, if soft, it means going to closer to 0, okay? And then here, if this peak is higher, so means there are a lot of cells trying to divide into two, which means the cancer is very aggressive, okay? And means this peak we did not can explain, but I mean this is how they explain this one, okay? And last example is about, let's say, lithography. So with AFM, you can do two kinds of lithography, either scratching, so you have a surface, you can make some scratch and write something, or by oxidation. Let's say you apply voltage at some position, and you can make oxidation of the surface. For example, this is an example of titanium, and we apply voltage on this position exactly, and this gives us, like, say, titanium dioxide. I mean, titanium dioxide is bigger than titanium. It will pop up of the surface, okay? And then when you scan again, you see this is the surface. It means the idea here that you have, let's say, this is a conductive material, and this is a non-conductive material. So I mean, if you want to make working at nanoscale, creating something fancy with conductive, non-conductive material, you can do it with the AFM, okay? And this is, means about I would say is about, let's say, maybe 10 nanometer, 20 nanometer, something like that. Yeah. And this is, let's say, thank you with your attention. How to apply? I mean, the AFM is just to make images for you. I mean, just if you want to make topography image to see these particles, you can see them with the AFM. I mean, the AFM cannot do any chemical interaction or anything for you. It cannot do reaction. Usually, AFM just you prepare your material and then you scan it with the AFM to see.
Topography, but on then see how or determine what happened for my part.
Yeah, what's happened? Then you make different images, different concentration, different preparation.
To the aim which I want.
Yeah.
In case of cancer, or for example, breast cancer, you said that the highest peak will indicate the progression or progression of cancer, which means highest peak indicate that stiffness.
Means is mean, let's say, lower stiffness and soft material, and they try to understand that. The soft material means that if you look to the molecule, or let's say the cell level, when you have cells, if the one cell was in cancer, one cell will divide it into two. And then if one cell wants to divide it, means the tissue has to be soft. And then when the tissue is soft, then the cell is divided into two. This is, let's say, what's happened for the cell for cancer. Now one cell, and then the cell will divide it into two.
The adhesion between cells indicates more stiffness.
No, stiffness. Stiffness is different than adhesion. Okay?
Because this is important for me.
Adhesion is different. Now we are just measuring the stiffness. So imagine here, when you come here, if you apply here, you see this is, let's say, soft, okay? And if you go here, this is hard. This you can see with the air. Just you have a cell, you come just to touch it and see really how it's reacting. That's it.
Which means this is maybe more applicable to solid tumor, for example, not for hematological malignancy as leukemia or blood cancer and so on.
I mean, yeah, and this is, let's say, tissue cancer.
Tissue cancer, solid
Tissue
tumor,
solid,
more specific for solid tumor.
Yeah, somehow.
Tissue grams coming from different points on the same cell or from different cells?
No, from this point it's coming from, let's say, I make an image of 70 micron on top of the cell. And this 70 micron, you have, let's say, is 100 or 200 points. And each point will give you some position, and then explain this.
So you try to scan healthy for different points?
Yeah, I mean, actually you scan to scan this is the concept of the part, and then you that histogram at different places, and then you can make average, of course, not just one.
Okay.
Can we measure any properties for solution or colloids?
You cannot measure solution.
Colloids,
Even like some particles.
emulsion. So
I mean, I show an example about, let's say, micelles. Usually they have, let's say, they're in solution micelle, and what you want to do, you always need to deposit them on the surface. Because, I mean, with AFM, if there is emulsion, liquid, I mean, you cannot scan a liquid. How do you want to scan something moving in liquid? That's why you need to fix them on the surface.
what type of mechanical properties can we know from this spectroscopy?
You can know two information, as I said. Is the stiffness, let's say, of the material, and you can measure also the adhesion force. Adhesion force being, let's say, you have different material, let's say, in polymers usually, which is used. Our stiffness is usually used in polymers when we fabricate polymers. In the stiffness, as I mentioned, so we have material here, you press, this is, let's say, soft here, let's say, and then if you press, let's say, here, this is hard. And this, you can see it with the air. And then again, let's say, this is, let's say, stiffness. And the adhesion force, let's say, sometimes when you come to material, the tip will stick on the surface. And the other material maybe will not stick. Okay? And then you can measure this also with the air.
What's the usual size of the sample used?
I mean, let's say, the real area what we measure with the AFM is maximum 100 micron. The air, but I mean, your sample can be
1 centimeter, 2 centimeter, 10 centimeter. And what you measure with AFM is just 100 micron of quality sample. We can measure at different place, but this is the maximum what we can measure.
That's why I'm trying to, in relation to the question raised by Dr. Isam, mechanical force, yes, but you also have electrical IV, so we can measure conductivity, and you also have magnetic information. In fact, to resume is anything that can produce the force, whether it's electric field, whether it's magnetic field, or direct force, direct mechanical force.
Let's say AFM, we can say this is always measuring surface.
Surface properties.
Surface
What's
properties.
the difference between microscope here and sim?
Okay, so there is difference between both. I mean, let's say samples give you always 2D images. 2D images. 2D images. AFM gives 3D images. So let's say if you want to measure the roughness, the height, the distance, you need an AFM. Listen, I mean, with AFM you can also measure in liquid. Let's say, if you want to measure, let's say, this cancer cell or something, you cannot measure them in vacuum. You have to keep them, let's say 37 degrees in liquid. Okay? Then you can measure with AFM in liquid. And what else? You can, let's say, magnetic properties and, let's say, electrical properties. You cannot do it with SEM. Okay? What else you can do? I mean,
Sample preparation.
simple preparation is much easier. I mean, it's, even you don't need any, let's say, if you have isolated sample, you don't need to make any coating with AFM. So you put it, you scan. Let's say you have glass, you put it, you can immediately start scanning. I mean, I think, let's say, honestly speaking, SEM is easier to handle because you put it, you get immediately an image. While with AFM, you have to find the right parameter for the tip when you are scanning the surface. And that's why you need, let's say, to be patient with AFM. You need patient and time. So that's
But the information is much
we have a different kind of information. We can get a lot of information.
it's much richer.
And I mean, in terms of resolution, AFM has higher resolution than AFM.
Software closed box or adjustable?
What's software what?
Closed box. I mean, I can adjust any or write any code. If I need to measure the thermal conductivity.
Yeah, this is another option.
It's an option that I think we need to buy.
No, this is inexpensive. I mean, thermal conductivity. No, you mean conductivity. What's thermal function? Conductivity is not measured to no. Thermal different than the conductivity. No. This is then you need, let's say, special tip, and that is measured, let's say, the temperature between tip and sample.
Yes.
And then for that you need a special tip, and then you need also special controller so that you can connect it to this system. And this is something additional.
Okay.
It's an option that we didn't buy. But we can.
By volt we can view equal A.
Yeah, I mean,
That's enough.
this is different.
It's direct. It's in direct.
And then software.
I mean, the software can measure you, let's say, IV curve, if you want to measure. This you can measure map of IV. Is this one?
Can we attach it?
No, I mean, I will reformulate the question because I think that I understood what you want. We have an image. We want to process it. Provided that this image is, I mean, how does it, is it materialized, this image?
Yeah.
Can I process, I mean, how can I process it?
Yeah, I mean, this is, when we will watch, I will show you how to like process and things like that.
Okay.
Information can be accessed.
How to access information?
Yeah, I mean, you have the image, then you have the software to analyze the images. And then this software, you can give access. Okay.
Information.
Yeah, I mean, it depends on what you want.
Or anything.
No, usually that's it. You have an image, you say, okay, I don't know, maybe I have this particle, I want to measure the height of this particle. You make, let's say, cross section, and then you measure the height and the width of the particle. Because you can do it with that. And this is.
Image. No calculation. No.
Then you have the spectra, and then you measure the height difference between these two lines. And then maybe you can have like different particles, you can make histogram and things like that, give you numbers.
First mode, which is contact mode. So as I explained, so we'll make like 5-minute presentation to show you, and then we will start measuring. And then now, so first, why we have to use contact mode on some case or not, and the application of contact mode. Okay, so the first question is which sample are suitable for contact mode. Means when you want to use AFM, you will say, okay, do I need to use contact mode? Do I need to do dynamic mode or what? So usually contact mode is used, let's say, for solid samples, let's say hard samples, with particles or anything well attached to the surface. I mean, something is fixed on the surface. That is not when you come, you move it. And let's say thin films, if you make like some coating, deposit something, you can use, let's say, contact mode to measure this. Okay? I mean, which sample, let's say, are not suitable to contact mode, let's say. I mean, not nanoparticles, let's say. I mean, let's say they can loosely bounded on the surface. Let's say you cannot use powders. You cannot say, because a lot of things say, okay, we have powder, we want to measure powder. You cannot measure powder like that. Usually you have to deposit on the surface, let's say not too hard, I mean, and not sticky. Let's say if it's not stable on the surface, you cannot use contact mode. Because if you have something, let's say this is particles. If it's not stable, when you come to scan, you move it, okay? And then you move it. I mean, if you move it on the surface, you cannot scan it. This we use dynamic mode for that, okay? I mean, this I showed you before. So I said we can measure any kind of interaction. So the interaction here between tip and sample is constant force, okay? And the sensor here is measuring the deflection of the laser on the detector. You see the detector when it go up and down. And then here, the feedback is the PID gain. So this will explain later what is this. Actually, this is to control the movement of the tip. And then you have the computer here to get your image, okay? So this is in contact mode, you have just constant force to measure between tip and sample, and you have the deflection. This is the only things we can measure. And this is just the parameter to control. I mean, you have, let's say, the laser on the detector, and then here, if you have the cantilever is bending, then, let's say, assuming you have particles, as I said, and then what's happened with the piezo, so it go up and down until to keep, sorry. So it will go up, and then it go up and down until, so the laser go back again to this position, okay? I mean, here it's okay, nothing. So, I mean, I will just briefly explain the PID gain on the IF. I mean, this is like proportional integral derivative. This is the electronics controller, okay? I mean, let's say if you take the example, the easiest example is, let's say, we have a fridge, okay? You say, okay, you have thermometer inside. You say the temperature now is, let's say, 8 degrees, okay? And you, let's say, your reference, you ask him, you ask the controller, let's say, when you change the temperature inside, you rotate it, let's say, assuming it's 5 degrees. So you want to that your refrigerator go to 5 degrees. And now the temperature is 8. Then what is the difference between this and this is, let's say, 3 degrees, okay? Then the controller, let's say, or the electronics will give an order to the motors to apply, let's say, power to cool down, okay? Then here it will give the power an order to do what? Cooler, go down. And then is the output again, and then you measure the temperature. Now it's, let's say, 7 degrees. Then it's here 5 still. Then it's the difference is 2. And then it's making, like, say, a loop, okay? And then it's measuring like that until it reaches the temperature we want, okay? Yeah, this is feedback control system. Yeah. I mean, what we usually use with AFM, we use 3 kinds of feedback. So we have proportional, integral, and derivative. Proportional is just measuring the difference between, let's say, this point minus output, so input minus output. Integral is, let's say, we can say like this is looking at now, so what's happened between my reference and what I set as a value, the difference. The integral is making the integration over the time from time 0 until time t, let's see, and then as a function of time. So you see this, and then you can measure what's happening in that. And derivative is the derivative as a function of time between these two values. Okay? I mean, with AFM, we usually use, we have to use these three together. Otherwise, or let's say PI minimum, because if you have just proportional, let's say, you say to the AFM, I want to have, let's say, 2 volt, for example. Okay? And now, let's say, it's maybe 1.9. At a certain point, it will go to 2 volt. I mean, if it go to 2 volt, the error is 0. When the error is 0, then the AFM will stop because he reached the error, the 0 error. And that's why we have the integral, because this you measure as a function of time, the difference from first point, second point, third point. Let's say if you make the integral over the time, it will not be 0, but it will be very close to 0. And that will make always the scanning all the time, because when you are scanning, it doesn't want to stop while scanning. So that's why we have this E inside. Okay? This will not go. This is okay. So, I mean, if you say now, what parameter we need to adjust with AFM, I mean, if you can tell me, in contact mode, what is the parameter we have? I mean, you should tell me. No, I mean the parameter we adjust. I mean, in contact mode, what is most important, we said? The force, constant force, okay? So that means we have the force, okay? Then we have also, second thing is the speed, so how fast we can scan the surface, plus PID gain controller, okay? That's all the parameter we can play with it to get the image. Okay? So that's all, okay? This is, okay. I mean, how to, let's say, to work with AFM. I mean, usually if we use higher force, we can damage the surface. Because, I mean, if you make too high force, we may start to scratch the surface, okay? I mean, and then higher gain mean like PID gain. So we have to adjust the right parameter for the PID. Because if you put too high parameter, so let's say if tip, let's say want to follow the surface, but if you put too much, then it start to make vibration. And may say, let's say, sort of overact or induce noise. I mean, you have to find this right parameter, okay? I mean, if you have, let's say, high gain, maybe a tip can, let's say, break, because, I mean, if you apply higher, also maybe it can break. And if you have force, higher force, you can scratch the surface, or the tip, you lose the resolution of the tip. So it depends which material is harder, the tip or the sample. So you can either destroy the surface or destroy the tip, okay? And so for that reason, with AFM, I mean, with AFM in contact mode, we start with lower force, and then we start to increase the force until we reach the right parameter, okay? So let's say we don't start, let's say, with 50 nanonewton, for example. We start maybe with 5, okay? And then we increase a little bit. I mean, this we'll see, okay, how we do that, okay? And I mean, of course, I mean, how long it takes to make a publication, it's most important is the sample preparation. So you have to prepare your sample in the right way. I mean, if you don't prepare your sample, you will not get a good image, okay? And then after that, you find the best parameter, best area on the surface, and then you get image. I mean, if you say in 1 month I can make a publication, that's not possible, I mean. So it needs some more time and invest a lot of time to get really to make a publication, okay? Yeah, so now we'll, I mean, this is, we show you this. For example, last things, I mean, sometimes you have the tip, when the tip is blunt, you will make topography image. And if you look to the image here, for example, here, you see, if you look to this, you see that all shapes are the same, okay? Rectangular is exactly all in the same direction. And actually what's happened here, the tip is lose resolution. And it's, instead of, let's say, be circular, now the tip is triangular. And what you are scanning here, you are not scanning the surface, but you are scanning the tip. Okay? So this is the image reflected of the tip. And that's you see, okay, my tip is not good. Okay? Yeah. So this is, let's say, about topography. So now we will really start using the system. So to use the system, we have, okay. Okay, so first, I mean, what I did, so just here, I installed the software on the computer, and so the software is called the NanoSurf C3000. I mean, you just click on it, it will open. Okay, I mean, we will install it on the computer, and then when it's open, you have this kind of, let's say, software. I mean, this software is just, let's say, I would say, is software to control the scan head. And then we have another software for data analysis. So now it's, let's say, to control and make, let's say, very basic things. And then if you want to do some advanced analysis, we have another software for that. Okay? Okay. So now we have the image here. So first of all, you see here, we can see if you have here file acquisition. Here you say, okay, I am in air or in liquid. Then I choose I am in air. Then here you say, okay, what modes I would like to measure is static mode. Okay, we start with static mode. We click on static mode. You can choose different mode, phase, contrast, other mode. We start with static mode. Okay, and then here you have here. So here you have image size. So we can have go from 10 micron or 0 up to 100 micron. Okay. Then here you have time per line. Let's say here is about 0.7 second per line. I mean, it can be, let's say, between 0.4 up to 2, 3. It depends on how big the structure. If you have very small structure, you can go fast. And if you have a huge structure, let's say, huge for AFM, let's say, more than 100, 200 nanometer or 500 nanometers, then you may need to go slower. Because you need that the tip is really follow up the surface. And if you go fast, you may not be able to follow. Okay? And then here you have the point per line. So that means now I have 256. So that means I will make 256 points in this direction and 256 points in this direction. So that means I have 256 lines times 256 lines. Okay? I can make it smaller. I mean, I can go to, let's say, 100, and I can go to 500, 1,000, or more. Okay? This is like pixel. You can make it. Okay, 256 times 256. And then here we have like rotation. So that means now I'm scanning, let's say, with 0, we are scanning like this. And if I put, for example, 90 degrees, we'll scan like that. Okay? So just how you change the angle scan. Let's say 45, then you scan like this. Okay? Then here we have the set point. This is set point is the force. As I said, in static, we have force, we have the time, and this is the scan size, and PID gain. Okay? That's all the parameter we play with the AFM for contact mode. Clear? Yeah. And now what we have to do now, we have to put a sample, and then we start scanning. Okay? So.
We have built-in default values. Built-in default values.
Yes. I mean, this is, let's say, now, yeah, this is the default value. But I mean, for each sample, you have to use. Yeah, I mean, is this you will see it how? I mean, now when we make image, I will see explain when you change why you change this parameter, why you increase this one, why you decrease this one, and then you will enable. So the isolation table of the system. So this is a vibration table, and this is inactive. Actually, if you see it, I mean, it's active. You see, it's floating actually. It means there is a piezo inside and coil, and make actively isolation the system in real time. Okay. And then you have, this is the scan head here. And here you can put your sample. It can be small, like less than 1 centimeter, and it can go up to 10 centimeter diameter, okay? And then you have here, actually under this one, you have the interface box. This is connected to the scan head. And then from this box is connected to the controller. The controller is here, okay? This is the controller controlling the scan head, okay? And the active vibration table, it has this on controller here, okay? This is the isolation controller. And then this isolation controller, so you switch it on, and then here, let's say, now the isolation is off. And when you switch it on, it's making the isolation of the table, okay, in real time. So when if you make like this, it will immediately isolate it. You will not see it on the AFM, okay? And then if you see here, you see there is air conditioning or ventilation. And the AFM is sensitive to this kind of vibration, because you are measuring image in nanoscales, let's say 100 or 500 nano, for example, or something. And if you feel this air, the AFM can feel it for sure. And then what we do, we have this acoustic isolation. You close it, and then you can close it from this side on the other side. Okay? And then you can shield the system against external perturbation. And one important thing is that when you have the system, it is important that, let's say, this part should be on a separate table than the computer, okay? So because when you even touch here or something, the AFM can feel this noise, okay? Any kind of noise, I mean, anything. I mean, so to get rid of noise, it's really important that this is separate, okay? So now what we will do, so I will take some samples, and we can start measuring on. I'll take, this is mine.
Do we have calibration samples?
Yes. There is 2 samples with AFM, usually, calibration. Let's say, I have here, like, say, sample holder. I mean, this is yours one. I mean, it's still new one. This is my old one. So usually this here. Usually what you do when you prepare your sample, let's say, if you have, let's say, a glass slide, for example, you can put it here, and then you can close it with this tool like that, and then you fix it. Or let's say, if you have, let's say, I don't know, silicon substrate, I don't know, mica, graphite, any kind of sample, what you do usually, you use, let's say, double tape, and let's say scotch, and let's say I have, let's say, double scotch, and then here it's, let's say, a little bit sticky. So then you put your sample on this. It should not be so much sticky, just to put it that it doesn't really move a little bit, okay? And then you put your sample, and then you scan the surface, okay? Relative, yes. Screw, yeah. I mean, what you have to see is that you are scanning an image of 100 micron. I mean, if you are on this 100 micron, if it's flat, it's fine. Okay? So I mean, you should not look to the sample in general, how it looks. You should look at the position where you are scanning. Okay? So, for example, let's say, if I, what is this? Look. Let's say, if you have any sample, I mean, let's say, if I have, let's say, this is, let's say, mica, for example, okay? Let's say, this is like for example, this is my sample, and then what I do, I mean, I put it on this here, and then just I fix it like this, okay? And my sample is fixed, okay? That's all. I mean, you don't need, and then I need to remove it again, so without destroy it. So that less here, it should not be like too much adhesive. Very slow adhesion is perfect, okay? And then I take it again. I can take it. You see that I can move it still. I mean, really. Then I can take it. Let's say. Hmm? No, this you don't need. I mean, this is just usually what I do. I mean, in most of the case, usually we put, let's say, double tape, and then we put on top the post-it. You know, the yellow post-it, this one, and then that is okay. That is perfect. Okay. And now, let's say, we will take standard sample. What we took? CD. Okay, so I will take, like, say, CD sample, and then we can start with this one, because it's a good example to show. I mean, I mean, this is, let's say, for me, this is like standard sample, and then you have, let's say, magnet here, and then just it's like magnetically attached. And this is something, but in real case, usually you don't have like that. So that's why you usually put tapes. Yeah. And then I have the sample here. So this is my sample already. I mean, this is standard. Now I have to put it and to start scanning, okay? So first I have to connect. Usually this is, let's say, I connect the sample to that sample holder because sometimes you have, let's say, electrostatic charge. And I mean, if you come here and just touch it, you can feel it. I mean, you can come and touch it really. And you will see that is just touch it and move it. You move your hand, and you see there is electrostatic charge because it's not grounded. So it's important to make it grounding the system. Yeah, yeah. You feel. So I mean, if you want to make a conductor, there.
We have a ground here.
Yeah, I mean, for now it's okay, but I mean, when you put your hand, you feel it really. So I mean, with this case, you will not be able to get any image. It's impossible. That's why what you do, I mean, I can show you to you when I remove the ground, and you will see that there is difference. I mean, what I'm doing is I'm trying to put the sample and the scanner at the same potential, and then it works, okay? So you have just here, you ground this, and you connect it. There is here on the scan head, there is in this side here, there is like hole here, and just you put, I mean, you just connect it like that. That's all. Okay, and then this is connected to here, and then you can also connect it. There is also the same one here on the AFM. Okay, and there is one here also. So you just put it here. Okay, okay, that's all. And then you ground this also. Okay, and then now everything is grounded. Okay? So this means now the isolation table, the sample, and the scan head at the same ground level. Okay? I mean, this is the first step. So we have prepared your sample, you come and you want to measure. Now what we have to do now, we have to put the tip. You know, we said that we have to measure with the tip and the sample. Okay? Yeah, I mean, yes, of course there is a safety. I mean, you have to look here. Now this come next now. There is, let's say, now there is like distance like this, okay? And then if you put this one, maybe the distance is like that. And then what you have here, you have, let's say, 3 screws. This you can go up here, and up there, okay? So you can go this up and down. Means there you go maybe, I think, maybe 2 centimeters or something like this, okay? So you can go up and down with these 3 screws. I mean, okay, and now, yeah, شكرا. Okay. لازم ايه هلا لازم يشتغلوا بايد. Okay. طيب. Okay. Now, so, I mean, you said that there is a tip, and we want to measure the surface with the tip. Okay. So there is here. This is the cantilever holder for the tip. Okay. Means there is a holder. The tip is here. I will show. I mean, I will show you this. Okay. So this is, let's say, the tools to exchange the cantilever. I mean, this is you have to practice. I mean, you will practice after me immediately. So usually here you open this like that, okay, and then you remove the tip and we put another one. Okay, I will show you. I mean, if you look here, you can see. You see this one here? Yes. Okay. I mean, if you can just rotate it if you want to see. And the tip, they looks like this. Okay, so this is like, say, this is the consumable for AFM. Okay, I mean, this is like consumable for AFM. I mean, you can see this. So this is something, let's say, the consumable you have to buy. I mean, you use. I mean, they will destroy a lot of this, and then you will start to complain and. I mean, if you look, I mean, from the back side, you will see there is like line and there is like peak, okay? This is the cantilever, okay? And this is, I mean, what we will see with the AFM. This is the tip here, and this is the cantilever. And the laser will come on this side, okay? I mean, if you look, if I open the, if I open this and you want you to look, if you see when I move it like that, you see, there is like line, needle or something. And then if you look really precise, you will see there is even like 200 or 300 micron something out, okay? So this is the tip on that. I mean, if you don't touch inside, just you can move a little bit, and then you can see light deflect, okay? This is the cantilever, okay? And if you want to see, I mean, you just move like this, and you see there is like line. I mean, okay? Okay? So, now how we, I mean, the most difficult part is how to exchange the cantilever, okay? This is the most part. I mean, I already destroy a lot of these things, okay? That's what I will do. So, I mean, someone has to practice because this, I mean, I will not be here next time to exchange it, okay? Okay. So, I have to exchange it. So, what I will do first, I open it, okay? Okay, and then I will come with, let's say I have this special tweezer. I mean, I come like this usually. I fix my hand because I should not shake. And then I come, let's say, perpendicular like that. I will take the cantilever, and then I will put again, okay? So for this, I will take, let's say, I mean, I have to have a box close to when I move it. So I will come with this cantilever. I mean, you can come and see. I mean, and then I take it and I put it. Okay? Yeah. I mean, now, okay. I mean, I will take, well, I have here tips, no? Okay. Yeah, I will give them some broken one to try with. Okay? So, I mean, I have this tip. I mean, I see that the line is like that, okay? Let me see that. So what I do, I come with this one here, take it like that, okay? I take it, okay? I mean, when I take it here, okay. Okay. I mean, first you have the cantilever. I mean, first you have to choose which direction is the right one. I mean, if you look, there is like line. You see the line. This line, it has to be always outside. Okay, outside, I mean this direction, okay? Outside, always. I mean, you see also here you have like line here, you see? So it has to be outside, okay? Yeah. You come with this one, you take it like this here. So this is like, say, when you come here, you have like, say, long area of interaction between the tip. You come, of course, I don't breathe anymore, you take it like that, okay? I mean, from here, it's easy. The most difficult is there, not here.
Could you please do it just in front of the...
I think he's scanning, no? I mean, he already do it. He already do it. Okay? I mean, if you look here to the tip, you see when you move like this, you see there is like small line brighting.
Yes.
Yeah.
Yes.
So this has to be outside.
Okay.
Okay? So when you take it like that, so my line is here. Okay? And then I put it here, also be like that, in air. Okay? Okay. So what I will do now, I take the tip, I go here, and now I want to put it inside, okay? I mean here, to put it inside, I mean, you have to come here to see it, okay? So I come here, and I put it in. Okay? I mean, this you have to come. Yeah, you come. Okay, you see. Look, stay here. Stay here. Stay here. Come here. Stay. Stop. Look. لا شفتها هتجربها هلا دورك. Okay? You take it here. I mean, if you look here, there is like 2 lines inside. Okay? You come like that. You put it. I mean. لا ما شفتهاش لازم نجربها. Okay? The tip is in.
المثلثة دي
هيدا التيب هي.
ده.
أوب. لحظة.
وهاو اوفن انت بتعملها يعني كل ما تبوظ ولا حسب؟
At least twice per week ها؟
عشان
اوكي؟
تصلحوا ويش.
يعني تبوظ تغيريها. اوكي؟ ماشي تشيل التيب هيك. حطها هيك. حطها بالسنتر يعني.
وهي ماجنتيك فبتمسك.
لا ما فيش ماجنتيك هون، ما في شيء. فيش ماجنتيك هيك. اوكي؟ هلا who want to exercise؟
he will act يعني هو اللي هيشغل الجهاز. لازم هو يبقى يجرب.
لازم يكون عنده good view. when عنده good view then it works. اوكي؟ طيب. لحظة أنا شوف. هيدي broken one مش مشكلة. it's all done. اوكي. طيب. first of all قرب هون. يشي تقرب هون قرب تفرجها. شايف؟ شايف؟ شيلها هيك.
ماشي. حطها تاني. احنا قاعدين نجرب بس يعني مش
ماشي؟
ماشي.
اوكي. هلا شو حتعمل
المشكلة في
بدي؟
الضغط يعني
ما فيش ضغط شيء يعني.
في ضغط
ضغط الكانتيليفر.
هو ده المشكلة. المشكلة ان هي تتكسر بسبب الضغط.
هلا انت مش ضروري تضغط عليها از كريزي يعني جاست تاتش
ان لو ضغطت جامد ممكن تتكسر.
مش كتير جامد. الضغط جامد بس مش كتير جامد. ماشي؟
فاهم.
اوكي. طيب you should try. عارف خليني اشوف انا. اوكي. شوي. اوكي you remove it. ما ضغطتش جامد وقت. ماشي؟ اوكي.
بنفس وعد.
ما لازم ضلك ضاغط.
ضغط
continuous. ماشي؟
قوة الضغط مشكلة.
We'll practice. I mean, if you want, you can practice. I mean, the most important that is one person can do it good, and then you can ask him to do it for you. I mean, okay, and he can learn also others how to do it. Okay. So now I will take it out. Okay, and then I will put a new one. So, I mean, what I will do now, I want to use like contact mode cantilever because we are in static or contact. And for this, there is, let's say, we have here a box, and this is written on the box is cont. Cont mean contact, okay? Al mean aluminium reflected, and G is mean growth. I mean, if you look to them, here there is like, you see there is like 2 lines inside, small lines, 1, 2, and another one perpendicular. This is we call actually alignment structure. So that means, let's say, when you put another one, we should go inside exactly. Inside this here, 1, 2, 3. I mean, this will go exactly inside this one. And then you have alignment structure. So when you put another one, it will fit exactly the same position. Okay? I mean, the advantage of this that when you move one, you put another one, it will be within 2 micron at the same position. So it will not move more than 2 micron. Okay? So that is easy. So when you remove one, if it's this one here, let's say the laser is here, you remove another, you put another one, it will be exactly more or less at the same position. Okay? So I take one. I fix it. Oops. And then now I want to fix it on the microscope, okay? When I rotate the microscope, I mean, you see there is laser here, you see it? Okay? And then when I rotate it, there is no laser, so just that's protection, okay? And then I take this side, and you see there is like also line here. Okay? So I take it also and put it in the same direction. As you see that I open it like this, and then I close it, and then I put it magnet. You see, there is nothing to do. Okay? Clear? No, I mean this is magnet interaction. Okay? You just move it, put it. No, I mean here there is something to laser that you don't touch your eye. I mean now if I rotate it again, I mean now you don't see the laser. But now the laser is on the cantilever. Okay? I mean if I move it here, you see the laser. Okay? This is the first step. Now is the second step. Second step now, you have the cantilever, you have the laser. I mean, what do you want usually to do? You want to put the laser here. Why? Because here, if this move a little bit up and down, so the laser reflected is more sensitive if it's here. Okay? So what we want to do, we put the laser here. To do this, so this is easy up to now, okay? Then you have like this one, and if you look here, there is like, there is 1, 2, 3, 4 holes, okay? And what you do usually, you just put like this inside, and you make a rotation, okay? So I will explain this for. I mean, I can maybe show it here. So if you look to the image here, I'm not sure if you see. I mean, if you look here, there is 1, you see, 2, 3, 4, okay? So 1 and 2 is to move, let's say this is the cantilever. 1 and 2 is to move the laser this direction and this direction. And 3 and 4 is to move the laser on the detector in this direction or this direction, okay? Okay? So here you move 1 is moving the laser this, like that, or like this. And 3 and 4 here is moving the laser on the detector in XY, okay? So how to do this? So, I mean here, usually I take it up and someone, I mean, fix it like this. I mean, you should not touch this, okay? Okay, so you take it like that, but without touching here. I mean, you should not touch this part, like this. And then I rotate. I mean, I will rotate now, so either in this direction or that direction. So now I will take it out because, so I will rotate in this direction. Because I mean now, so this is the cantilever. I mean, if I rotate in this direction, I will go inside. If I rotate, go like that, okay? So now if I rotate like this, I will go in. If I rotate like that, I will go out. Clear? Okay. So what I will do now, I will go out. I mean, if I, this is here. I mean, if I rotate like this, it's going in. If I rotate like that, it's going out. I mean, now I know because I know. I will explain. You will see now. I mean, now there is, we have no, I mean, there is no laser. I mean, I want to take it outside of the cantilever. I mean, so let's say this is my cantilever, and the laser is somewhere here. I mean, I will rotate in this direction, so I will make like that, okay? So, I mean, I take like this, and I'll go out. And you see now, I see the laser, okay? So, I mean, I see the laser now when I rotate it like this, okay? You see the laser spot, it's here. So, if I go again inside, the laser disappears, okay? So, the laser, yes, yes. Exactly. In the position 1, okay? I mean, because I mean, one is go here, let's say, and if you are here, you are at the top of the cantilever, exactly. But I mean, sometimes you are like this, and then you go, maybe you touch here. This I will explain later, okay? But now we start with easy things. So you are here, you come like that, it disappears. That means I am at the end of the cantilever, okay? It's alignment, yeah, it's alignment. And now, to be sure, you are sure that on the cantilever, I can move like this, and you will see that, I mean, this has like width of 30 or 40 micron, okay? So it's not too large. And then when I take position 2, so I put in position 2, I mean, I can rotate in left or side, it doesn't matter, okay? And then I will see, I will rotate in left side, you see, I see the laser. And then if I rotate in this direction now, laser disappear. If I continue in this direction, it'll appear again, okay? So then I go back, I put it on in the middle, okay? Clear? This is position 1 and 2. And then position 3 and 4, we do it on the computer. That is easier. Then you open the software. There is here a laser alignment laser. You click on the bottom alignment laser. And then you take, let's say, position 3. And then if I move up and down, you will see that the green button will go up. You see this is going up and down, okay? And then I want to put it in the center, okay? And then position 4, left or right. So I can go in this direction, you see, or I can in the other direction. I mean, the ideal is to put it in the center, okay? I mean, that is already, okay, good, okay? I mean, if you look here, I mean, if you look on the image, you see there is here, downstairs here. You see that normal deflection is 1% and lateral deflection is 0.5%, which is, I mean, ideal is 0%, okay? But I mean, here it is 0.5, this is already, yeah, okay? And this is the center. And then you see here, this point here is the laser working point. I mean, if this go to 100, means there is no laser on the detector. Okay, there is no light arriving to the detector. And if it's below 50 or 50, between the green one, there is the mean laser on the detector. I mean, this means here, let's say the power of the laser. I mean, if there is no laser on the detector, so the power will increase of the laser because he thinks that he needs more power to go to the detector, okay? And so low power means even better, okay? And now it's done, so I make it close. I mean, what I can do also for you, to show you, so if I go up, I take this here, let's say, for any reason, I put it again, and then I want to see again, you will see that it's exactly at the same position, okay? So you see that it's still at the same position, okay? So you don't need really, okay. And then now it's closed. So now, let's say we change the cantilever, we adjust the laser. I mean, you have to also, maybe this afternoon after 5 we practice more, okay? And now what we do, we put a sample and we start scanning, okay? So, I mean, if you want, somebody want to see the cantilever, now you can come and see from here. We have actually a top view here and side view from that side. So from top, you see the cantilever like that, and then you have from side, you see like 45 degrees. And then when you want to make the approach, when you are very close, you see there is, let's say, shadow. Okay? And this shadow, you can see it. I mean, of course, we will touch at the end. Okay? And then now we try to be very close. And then when we see very close, then we stop and we make the automatic approach. Okay? So first, to put the sample, usually I put like, I look from one side, I approach from one side, and I look from the other side to see the distance between tip and sample, okay? I move, and then I see, okay, is the height is too big, is too high or not too high, so I have to see. So if I look now, I mean somebody, maybe you should come look. I mean, طلع من هون وشوف العين. شايف مبين السامبل؟ واضح؟ والليزر مش مهم، المهم التيب، شايفه؟ وهذه العينه هون. If I approach more, I will touch clear. So what I do then, I move up here, and let's say rotate 3 at the same time. Okay? Go up, up, and up. Okay?
عشان اعرف حضرتك.
Up, up, let's say up. And now I think it's okay. So I move it, let's say, you see?
until it
Okay, you see now, I mean, I will touch or not? I will not touch. I mean, it's like about half millimeter now. You see it? Okay. So you look, you see, okay, I am far from the surface. And this is my sample. And look, if you look from here now, if you look here inside this one, you see the tip?
ده.
لا. قرب عينك، قرب بعد. You see it. خط أسود. Okay?
خط الاسود ده.
Okay. Head the top view. Okay, you can see it. Yeah. Hold top view. Wait a minute, I will show you. You see it? قرب more. Approach more. Okay? Ibra. Okay. So this is the sample now. You see it, and you see the tip. Okay? And you can see also the side view. If you look from this side here, okay, you have to make like this. You see like 45 degrees. 45 درجة up. You see it? So you can see from this the side view. You see it? شايفها؟ 45 درجة. وطي عينك بعد.
كده بدأت.
You see it now? Okay. And now what we have to do now, we have to approach. Okay? So, I mean, I will look from this side, and I see, okay, how far I am. I mean, now you see this is like, I would say maybe 3 millimeter. I mean, the motor can move just 1 millimeter. Okay? So what does it mean? I am too far. لازم أقربها. So what I do, I move here, one. Okay?
في الرينج بتاع المين.
Okay. And now it's okay. I mean, if you look now from side view, I mean, now I'm very close. What do you see? Do you see a shadow? Okay? I mean, you can look to the shadow. I mean, stay, look. If I move, you see the shadow is approaching, no? And now if I retract, you see it? Okay. Clear? Okay. Do you see now the shadow? If I move now, you should see. You see it? Okay. Clear? شايفها؟ When you see the shadow, you see the cantilever. Close. You see it. Okay. This is the top view here. You see the cantilever, Ibra. Okay. And now, if you look to the 45 degrees, now you have to make 45. You have to look like this. Okay. You see it? You see the shadow and you see the cantilever. I mean, if you stay, look, I will make move. You see, it's moving. The shadow is approaching. Clear? And then if you go back now. Clear? So. You can approach it to see it more. You see the top view? Okay? And now if you look from this side like this you have to make. You see? And then if I advance, you see this is moving? And now if I retract it. Okay? Okay. Okay. بالside view. This is the substrate. Let's say this is the surface, and this is the cantilever. If you make like so close like that, you see the shadow. The shadow is the sample. Okay, you see this is the sample, and then when you are closing more, you see that will touch something like that. When you see it like this, 45 degrees. Okay. Okay. So now I will approach until this shadow will touch really the surface. I mean very close, and then I make the final approach. Okay. Now I click on advanced, and now I move just the motor, okay? I mean, if you look now to the 45 degrees, you see how close they are. ماشي؟ والخيال، شايف الخيال؟ خطين.
اللي حواليه.
واحد توب فيو واحد سايد. Very close, they are very close.
في فوق من كده.
ايه في واحد من فوق وفي واحد من تحت.
والخط قريب منها قوي.
ايوه هودي الاثنين. اوكي؟ بس بالتوب فيو ما تشوفه. من سايد فيو. يمين. في واحد هيك وواحد هيك. اوكي؟ واضحة؟ Clear? I mean, if I go up a little bit, you will see. The two line is okay. 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 And now I will click. So now I close. Okay. And now I click automatic approach. So there is his bottom approach, and now it will do approach. Okay. So now here is showing moving, and now it's moving slowly to the surface, to the final. So I mean, if you are too far, it may take like 5 minutes, and if you are very close, it may take like 1 minute. Okay. So just, and when it reaches the final destination, it will make approach done. Okay. I mean, here is moving here. You see here is moving. Is it moving? And this is moving. Okay, slowly. So now approach is done. Okay. So when it's finished, he wrote approach done. Okay? And now what I want to do, I want to start scanning. So to make start scanning, there is like start button here. Okay? And when I click start button, it start. Okay? So what we will do now, I mean here, I have like say image size, let's say 10 micron. I mean I will make it a little bit, maybe 20 now. Time per line is about 0.8 second, 256. Now what is important is the set point. Is 20 Newton, nanonewton, okay? And this is, let's say, the default parameter, okay? And it is okay for this sample, it's okay, I know. But I mean, we'll see how we do. I mean, here is a P gain, let's say, I put it, maybe 1,000. I mean, usually the value of PID gain is between 500 to, let's say, 3,000, something like that. I mean, usually 1,000, 1,500, 2,000, something like that, okay? And then what we do now, I just click start. So if you see now, so this is, I mean, I'm scanning the surface here, okay? And this is the line. So here, this is, down here is the line by line, what's going up here. You see this one here, the black part, is going up, okay? And now is scanning the surface. Hmm?
Every line
It's scanning line by line, okay?
will be saved, every line.
Is it saved in the image? When it's finished, it will give you that whole image saved. Okay? So now, I mean, it's line by line.
Why left and right?
What?
Left and right screens.
Here, yeah. I will come to this. So now I'm start scanning, okay? Here you have the topography image, and this is the deflection, you know? This is, for you, this is like error image, okay? I mean, error image, yeah. I mean, this is the deflection of the laser on the detector. I mean, we said that it has to be, let's say, at fixed position, because it's go up and down. Because here, let's say, you have some structure here, and this structure, the cantilever make deflection, okay? And this is the deflection image. We always try to keep that we don't see anything in this image, okay? At least to make it as minimum as possible, okay? To do this, we have to adjust the PID gain and things like that, okay? So now we just start, and then we start to adjust, optimize the parameter, okay? So now, I mean, this is the force. And let's say, I make line fit here first, okay. So, I will start. No, while scanning. When you are scanning, you adjust the parameter. Okay? So, what we do first? I mean, if you look, okay. First thing, if you look on the image here, let's say on the line, you see there is two lines. One is black and one is white. You see them? These two lines has to be as close as possible to each other. Okay? The black line is like, say, the forward scan, and the back line is the backward scan. Because, I mean, what it's doing with AFM, it scan like this, like that, like this, like that. Okay? And then there is no reason that these two lines are different. Okay? So it should be the same. I mean, usually you try to put them as close as possible. I mean, you see now they are really very close. I mean, almost one. I mean, which is fine. Okay? Okay. So this is the first step. The second step, what you do, if you look to this image and you try to see, I mean, this is like error. What you try to do usually to minimize this error. To do this, you have to adjust this value here. Okay? So, I mean, let's say now what we do first, if I have the force of 20 Newton, okay? What I said in my presentation, the lower force is the best because we don't want to destroy the surface. So I will go from here to 0, okay? So what's happened now? You see there is nothing anymore. So that means I lose contact with the surface. So the tip is not touching anymore the surface, okay? Then, I mean, I can increase it, let's say. I mean, sometimes for some sample, I really put 0 or even minus, and it's still scanning because there is adhesion force between tip and sample. And let's say I put, let's say, something like 5. Now you will see what's happened. Nothing. Maybe I put maybe 10. Shit. I lose contact, I think. Stop. Approach. Huh? Yeah, we can change, but I just try to understand what's happening. Okay. So let's say I go now to 15, and you see that it's still scanning. So that means 20 is what, let's say, already too much, so I was trying, I'm destroying the surface, I mean, or applying too much forces. But if you apply too low forces, maybe you will see that the two lines are not anymore close to each other, okay? So let's say if we keep it now, means 15 is okay for this kind of sample is okay. I mean, let's say I'll put 10, and we'll see if it's still working. So 10 is working, okay. But if you look now to that two line, you see there is a little small shift between these two lines now. You see it? I mean, if you put this and you compare to 20, there was closer. I mean, also the force is also playing. So if here I reduce the, let's say I go faster. I will go, let's say, to 0.5. So, and you see this, I mean, yeah, the two line is here scanning. And if you look to the amplitude here, yeah, it's too high. So, I mean, it's not seeing really too much, but okay. Let's say if I go fast like this. Now, if you see now, you see these two lines are really difference between these two lines. Okay? So now you see when I put this speed, you see that these two lines they are a big difference. So you have to adjust the parameter between the speed and the force and the PID again in order to keep these two lines close. Okay? So now you see now when I put, let's say, 0.5, you see that the two lines are very close. Next step now is I want to adjust this image. I don't want to see anything on this image. Okay? So what I do first, I will increase the gain here. Means the most sensitive is the eye gain. Okay? So I will go, let's say, to maybe 2000. Okay? And now when I increase the gain, you see that these two lines, they are closer, really very close, more. And you see that it's really sharper. I mean, yeah. So, I mean, maybe we wait a little bit, you will see. I mean, you look here and look to this one here. I mean, here we see it more than here. Clear or not? Yeah? So, means now my image is much better because I don't want to see anything here. I mean, you see here, this is brighter than here. And this is clear, okay? I mean, what I can do also, I can try to adjust the other one. Okay? That's it. I mean, around 2000 now. And then you start scanning. I mean, now what I don't see that. I mean, now I increase maybe too much the scan. I mean, if I increase here more, maybe I will show you. If you look to this line now, you see there is a lot of small things. You see that? And if you look in the image here, you see, do you see something here? I'm not sure if you see it there. Yeah, you see here, you see this small here, things like that. And if you look here on this image, you see it better. Wait a minute. I make it big for you. Look. Okay. Yeah. Okay. If you look now to this image here on the left, you see this here. You see small noise. You see the noise here. I mean, here in this here is shown better here on the camera. You see here, you don't see a little bit, but here we see the noise here. Okay. And this noise, because I have a too much high feedback. So to reduce this noise here, I just need to reduce this gain here, okay? Okay, so, I mean, if you look even to the line, okay. I mean, if you look to the line here, down here, you see this line here, you see there is a lot of small things. You see it? Like small, like that. I mean, if I reduce here, you will see that it will go disappear. or become less important. You see now. Do you see now the line is really change its shape? Okay? So now I go down, and then I will scan the surface. We almost finish for this contact mode, okay? So, is it clear for you? I mean, we have to play with the parameter, so we have to play with the force, with the image, with the time, and then with the here with the force and the PID gain. Okay? And then after that, we'll come to the analysis, how we analyze the image and things like that. Okay? So now we can keep it running and we can go on cam and no problem. هلا وين في مين اجى جديد؟ راشد غنوشي ايش في ده غنوشي؟ اوكي. Right. So, before we start the new mode, so I will just show you if you have an image, let's say what we can do with this image, briefly, and then we can go later more. If you have here, let's say I go to gallery, I open an image. Okay? I have this image here. When you say, okay, I want this image in 3D, you just click here, and then you say here, okay, instead of make it a color map here, you do it in 3D view. Then you have it in 3D. Okay, maybe now just make it big in pixels, maybe. And you can have it, let's say, in 3D view. Maybe you can rotate it to see, for example, or, okay? Let's say this is, for example, if you want to have it in 3D view, for example, okay? I mean, what is important, let's say if you have it here like that, I mean, as I said, this means higher, and this is lower, okay? And you go, let's say here you have like analysis, and create cross section, okay? I mean, I can cut any line in any direction I want. Let's say if I want, okay, I will take line in this direction, okay? And then I have the line. I click, I have the line here, okay? Then you can say, okay, what is the height of this one? Then you measure here this, measure distance, and then you measure, let's say, from here to here, and this is give you the height, and it should be here. And then let's say the height is about 125 nanometers, okay, for example. And you can say, okay, what is the length, let's say, from here to here, and then you can make like measure length, and then you can measure, let's say, the distance, for example, from here to here, for example, okay. And then here you have the length, like say 3 micron, 4 micron, or etc. Okay.
Can I insert coordinates?
What do you mean by coordinates?
I mean, if I want to make a cross section at the middle.
Anywhere you can make. Anywhere. I mean, usually, I mean, you can create a cross section. Let's say you want to have your section here. You can make it like here, okay? Like that. I mean, here, this is the position here. You have it here. And then, when you have the line here, let's say this is the length, and then you make cut line, and then this you have your line. I mean, you can save the line if you want to open it with, let's say, Excel or any kind. You can save it as you want, or as image or whatever. Okay? And this is, let's say, let's start now with the basic things. So this is, let's say. Then you can have, I mean, we have another software, which we come later. You can make like filtering, for example. If you have some noise on the image, you can make, let's say, here very fast filtering. And then if you compare, let's say, these two, you see the line here. Wait a minute. Make it smaller, let it fit. I mean, if you look to this image here, I don't see it here. I mean, there is line here somehow. If you have, let's say, some noise, I mean, you can make some filtering, applying some, let's say, noise filter here, and you see this, it can become better. I mean, yeah. I mean, you see there was a line here, you don't see it anymore. I'm not sure if it's clear there or not. So you can, let's say, if you go to the original image, and let's say there is a line here, actually. And I mean, in my computer, we see it better. And here's the line, it's here. Yeah, I mean, in the topography, when you correct it here, you see that, no. So just make, if you have some filter, you can make filtering. You can make also, let's say, I mean, this will come later, correcting background. I mean, if the surface is not flat, you can make some correction and other things, okay? And this will come later, for when we have something more complicated. And then, so now we go, let's say, we go to dynamic mode. And now, so here I was in air. Now I choose here dynamic mode, or let's say you can choose dynamic and phase. I can do it at the same time. So I will take, let's say, phase. Phase means it will give me dynamic and phase. Okay, it will give you two information. And then here you have to select the cantilever. I mean, this is, I will use this one is tapping 190. I mean, this is written on the box. What is it? The model. And then here I have different parameter for tapping mode. So now I will explain what is tapping mode. No, we will change the cantilever for tapping mode. So the cantilever for contacts, they are different than the cantilever for tapping mode or for different mode. For dynamic, it's different than for electrical, for magnetic. So they are different modes, or different models. Okay. So if you have here, I mean, I will explain now dynamic mode. So this morning I said dynamic mode is making oscillation. Okay. So I mean, what kind of samples they are suitable for dynamic mode? Usually we have, let's say, rough sample, let's say powders, soft material, and let's say materials that are not stable on the surface. Okay? Okay? I mean, and I would say like more than 90% of people using this mode when they do images. They start immediately with this mode. Okay? On 90% of population, I mean, of experience. I mean, let's say nanoparticles, solid, rough sample, soft sample. I mean, sample also in liquid. If you want to measure sample in liquid, usually you use dynamic mode for that. Okay? So, I mean, how it works, so as we said this morning, you have here cantilever, but now making oscillation. And then you measure the oscillation on the detector. So you measure the amplitude on the detector. Okay? It's better also. We should put it always at the center. It's better. Because if you make oscillation, because the detector, I mean, it has like, I think maybe 2 micron deflection or something. If not in the center, maybe it go out of the range. Okay? So you put it in the center, it's the best. So, I mean, how it works now? So, we have a sensor, and then we measure the interaction. So this time the interaction is constant amplitude. This morning it was constant force. Okay? And the sensor, I mean, this morning it was the deflection, and here we are measuring the amplitude. Okay? And then we have the PID gain, the same, and then the controller. So the only thing changed is the constant, the amplitude now. Okay? So it's more or less the same. So how it works, if you look now, we have cantilever with oscillation. This is, let's say, the amplitude oscillation. And when we are approaching to the surface, let's say, so you are very close to the surface, then you can see that at the beginning, this is what we call, let's say, free vibration amplitude. So this is in air, free vibration. Okay? But when we are closing to the surface, I mean, you are close, this amplitude, it will reduce because it's touching some surface. So then you have, let's say, amplitude reduction. Okay? Then when you are closing to the surface, let's say, maybe it's reduced by 50%, 70%, 60%, it depends. So we have, let's say, what we call amplitude reduction. Okay? Then the amplitude, instead of being, I don't know, maybe 1 volt, for example, now it's like maybe half volt. Okay? So we have amplitude that is reduced. because actually simply we are touching the surface. We cannot go further down. Okay? So, and this is if we can make it in a spectra. So if you look to this, if you look here, so this is the free vibration amplitude. Okay? This is the spectra, the standard one in air. So there is no touching. We are far from the surface. Okay? This is resonance peak. I mean, it depends on the excitation you put. Let's say this is vibration. You excite the tip. You say, okay. Let's say in this case, I say, okay, my vibration is 2 volt. So that is the amplitude is 2 volt. Okay. Let's take it in this way. And then this is in air. So the first one here is in air. I mean, you are not. I am far from the surface. And usually with AFM, we work at this point here. Okay. This is, let's say, the free vibration. I mean, this reduction is because we said that when we are touching the surface, the peak will shift. Okay? So that's why we put it at this position. And now, what's happened when I'm touching the surface? So the amplitude is reduced. Okay? And this is, we call it the set point. Okay? And this in the contact mode, that was force in nanonewton. And here it will be like percentage. It will be set point, it will be percentage of the free vibration amplitude. So for example, how much is this reduced with respect to this one? Is it 20%, 50%, 60% reduction? Okay? And this is give us the amplitude, let's say the set point. No, it means the lower you are more closer to the surface. I mean, let's say if you are, I mean here, if, I mean lower what? You mean lower amplitude, or, I mean if you have lower amplitude, I mean you are going very close to the surface more. When you have, this is the amplitude, and then you are making closer, so you are approaching more the surface. I mean this is proportional to the roughness, let's say, or the structure. I mean if you have, let's say, structure of 500 nanometer, you may need to go like to make maybe, let's say, 5 volt, for example. If you have like structure of 5 nanometers, maybe then you may go to like 1 volt or lower. So to be close to this structure. Okay? So this amplitude is directly related to the roughness of the surface. Okay? Because I mean this oscillation is like reflected some nanometers height. Okay? I mean if you say which parameter we can adjust with the dynamic mode, so means you have, as before, PID gain. We have also the time, as before. What is changed? I mean, we have also, the set point. Like in contact mode, we have the set point. It was force. And here, what additional parameter we have? The free vibration amplitude, the excitation of the tip, because we can excite it very high, very low, as we want. Okay. And then we have, of course, when you have fabrication, we have also show frequency also. When you have amplitude, you have also frequency. Okay? So, if we compare to contact mode, so, I mean, the set point now, it will be in percentage of the free vibration amplitude. Okay? So this will see, when we see it, we'll understand it easy. So let's say if we have, let's say, 5 volt, the free vibration amplitude, and here we put like 60%. This is like our working point, 60% of 5. Okay? Then PID, speed, and frequency. While with contact mode, there was set point in nanonewton, in force. Okay? Yeah, I mean how we adjust the parameter. So just to show you, if we say just for the free amplitude, okay. If you have, as I said, if you have high structure, then we have to have high free amplitude. Okay? If we have small structure, the small Z-range structure in height, then we need small amplitude. Okay? And then the set point, how we adjust the set point, there is two things. One is the free amplitude, now the set point. If we have high value of the set point, mean we are, let's say, have gentle contact or soft contact. For example, because we have sometimes different kind of soft material. And when you have different kind of soft material, the set point, if you have, let's say, solid material, we can put a set point of 50%, for example. If you are working, let's say, with DNA or maybe softer than DNA, for example, then you may need to go with this set point to, let's say, 90%, 95%. It's, if you imagine, let's say, I am touching the surface like that, or I'm touching the surface like this, okay? So, I mean, if you go harder, if the surface is hard, it's fine. But when you have, let's say, soft material, maybe then you have to go just gentle to the surface. And that's why you increase the set point, okay? That is, I mean, how you usually do. First, you see the amplitude to see how big they are the structure, and then you want to see how stable are the structure. Then you play with the set point. Okay? Clear? I mean, it will touch the surface, cannot penetrate, just touch the surface. Okay? I mean, go like this, touch like that, and then go up, down. I mean, you are scanning a line, and then we have like frequencies about maybe 150 kilohertz. Okay? So this is like 150 kilohertz, imagine, and then you are scanning the surface with like maybe 1 hertz. So from 1 hertz compared to 170 kilohertz, I mean, it's very slow, the 1 hertz. Okay? And the tip is touching, sometimes it's touching like that, just touching. It's I call it, tapping mode, so it touches from time to time, or sometimes it's not touching. It depends really on the set point. I mean, if you have, let's say, if you have, let's say, low set point, maybe you are touching like that, and maybe if you increase the set point, maybe after that, maybe you will not just feel the surface, you know? Yeah. It will not penetrate, it's just the surface. It will see the surface, how it looks. It will not what? No, I mean, it will not penetrate the surface because, I mean, you have the feedback, you will control everything. I mean, you will destroy the tip if you touch the surface, you will destroy the tip. I mean, if you touch it too much, let's say. This is experimental. You will see how we measure this and what we use. I mean, let's say, in contact mode, we said that we don't want to see anything in deflection. And we said also that the forward and the backward, they have to be as close as possible. Clear? And in the dynamic mode, we have also the amplitude and also forward and backward. So this is, we'll see now how. Okay? So what we do now, we will change the tip. We'll put, let's say, another kind of tip. So again, I will change the cantilever as I made before this morning. I mean, I have, let's say, here, contact cantilever. I mean, and now I want to use tapping. So I have to change the tips. I mean, the mainly difference is let's say, here the force constant is 0.2 Newton per meter, and the frequency is like 30 kilohertz. And the one I will use now, it has a frequency of 150 kilohertz. Okay? And maybe here spring constant is like 50. Okay, so it's much bigger. Okay? Mm-hmm. No, it's the same way. I will see. So I put a new cantilever, and I will take, let's say, another sample, okay? I have, let's say, gold nanoparticles. Oops.
احنا عاملينها اوريدي على جهاز ده فوليوم يعني فوليوم
Okay. كيف بدك how do you want to measure this? How do you want to measure this? How you want to measure this? No. I mean, this is, they are not on the surface. I mean, did you measure this with AFM?
Yes, of course. Not me, doctor.
It was like this.
Powder.
This is powders.
We have double ten.
Okay.
What it is? Difficult to measure?
I mean, this is too small. I mean, I have to see what is this. I mean, how. Maybe later we can try this. Not now. Okay. Okay. So as the same way as this morning, I put sample. I put it under the AFM. And then I look, I mean, and you see the distance, it's far. Okay? Now, what I have to do first is to adjust the laser. Okay? So, as I made this morning, if I take it, I mean, if I take it up now, I see the laser. Okay? So, first step, I will take position 1. Okay? And I will go inside. So that means I will go like this. Okay? So, I rotate. Laser disappear. Okay? So that means I am on the cantilever. Okay? Then I take position 2, go right or left to make it perfect. Out on the cantilever, completely out. Okay? And you see it here. Out on the cantilever, out. I put on the cantilever. Clear? Then the laser is adjusted. Then 3 and 4, you go here, you click on laser alignment, and then you make it. And just go down a little bit here. You go like left. Okay. Clear? Now I put my sample under the AFM. Okay. And now what I want to do now, so I approach as before, okay? And now, first step is, I mean, this is just, I will show it to you to explain you what's really going on. There is frequency sweep, okay? So I make cross sweep. So usually this is like making excitation of the cantilever to find the resonance peak. I mean, if you look to here, you see there is here maximum, okay? This is actually the resonance peak is here, okay? This is the peak I'm looking for, okay? Okay, this is about like 150 kilohertz, okay? I mean, usually what's happened, let's say 500 millivolt. Okay. Okay. I make cross sweep. Then I have here, let's say, the maximum. And usually what's happened here, if I make, let's say, auto frequency sweep, usually he will try to find this resonance peak and zoom inside this peak, okay? When he's making excitation, trying to find this maximum. This is the maximum peak, okay? And then he's trying to work close to this maximum peak. So if you look, so this is the amplitude, free vibration amplitude, okay? And this is, here's the point where I said, okay, we work like 20% below the maximum peak. But when we are in touch with the surface, set point, set. So now I am ask him, let's say, I want my free vibration amplitude of almost 2 volt, okay? This is 1.96 volt, okay? This is my free vibration amplitude. And this is the amplitude, and this down is the phase, okay? Okay? So I ask him to 2 volt. Let's say 2 volt is, let's say, we can say that default parameter is 2 volt. Okay? We set it. Then what we want to do, here we have the image size times, this is doesn't change as before, it's the same. The only thing it changes is the set point. So now the set point is 50% of the free vibration, which is 2 volt. So that means my working point, the amplitude I want now is 1 volt when you are touch the surface. Okay? So now what we do, we just make approach. Okay? And then when approach is done, then we start measuring and then we see what's happening. Okay? Now I click approach. So now what he's doing, he's trying to find this resonance peak and trying to find the maximum. And now it's moving. You see that it's moving now. And we have just to wait until it touches the cantilever, the surface. What's happened now is trying to reach, let's say, an amplitude of 100 millivolts. Okay? Then once the amplitude is 100 millivolts, then it will stop. Okay. Okay.
Can I hold?
Yeah, you can work. I mean, but I mean, if you have some air, it's not good. So approach is done. Then I will start. Okay, now it works. Okay, so now I'm measuring, like, say, some particles on the surface. Okay. So okay, so now I have, when I start measuring, so as before, we said, like, we have to have, let's say, forward and backward as close as possible. This, we look here in this line here. We see that these two lines, they are close, okay? And then to have forward, backward as good as possible, we have to play with PID gain, okay? I mean, like, say, this morning I put like around 2,000. We can say, okay, it could be okay around this value, okay? This is the first thing. Then I put here, let's say, maybe 1,800, okay? Then, second step, now what we want to do is the set point. I mean, this morning we were saying, okay, whether the force is correct or not. I mean, here I'm measuring, let's say, some particles. Usually 50% is already too much when you're touching the surface. So usually when you start measuring, you start like 60% in general, okay? 60% as beginning. And I mean, I increase this to 60%. And then, let's say, as a minimum value, maybe I can go even to 65. It's, let's say, this is as a beginning value is okay. And now, I want to, let's say, optimize my parameter. So I look to the topography image, and here, I mean, this morning, this was the second one, it was deflection. Now it's amplitude. And we are working at constant amplitude. So that means in this image, I should not see anything, okay? I mean, if you look to the line here, you see the line is, let's say, almost constant, okay? I mean, in reality, you will always see something, but I mean, always we want to have, let's say, as minimum as possible of something, of error. So, I mean, if you look to that image here, so if you look to these particles, I mean, if you see here is 15 nanometer minus, and let's say this is 0, okay? So this particles is about 5-6 nanometer height, okay? So what, then I'm using, let's say, 2 volt vibration amplitude. And let's say, if you can say, okay, 2 volt is representing, let's say, 200 nanometers. And I'm measuring particles of 6 nanometer. That means I am too far from the surface. What I can do, I can reduce the vibration amplitude maybe to the half, let's say. I mean, I can go here, let's say, 500, so I mean 1.5, okay? And now it will should adjust it again. Wait a minute, didn't like it. And it's still working, yeah. I mean, it is still here measuring. Yeah, I have just to. Okay. Okay. So now I reduce my amplitude, okay? And then if we are measuring some surface and then you see, let's say, there is some interaction. And what you can do in this case, I mean, if you have soft material, we increase the set point, okay? I mean, what I want to explain, maybe I have to use another more difficult sample to show you. I mean, sometimes you see here there is like some peaks. You see this line? And this line should not go to 0. I mean, now we are far from 0. Let's say, this is my baseline. And this line is now, let's say, around, this is like 475. This is 1.5. So here I am, let's say, 65% of 15. I mean, it's around 13, something like that. So I'm here, this is 13. If here, let's say, I put 70, you will see that this line will go up. You see it? It's go up. Okay? Yeah, the line here. And sometimes when you have, let's say, particles here, you see, there is, or here particles, you see there is like small peaks here. I mean, these peaks should not touch 0. If touch 0 means that the tip is touching the surface and I'm destroying my tip. Okay? So this, I mean, here you see, I mean, okay, here I am about 1 and 0 is somewhere too far. So that means I can really go closer to the surface more, okay, because I'm too far. Then I can put here, let's say, maybe 1, put 1 volt. Then I am, it should be now closer to the surface. You see? Now I go down here, because this is now 70% of 1 volt is, I mean, 700 millivolts, or 0.7 volts. And I am here 0.7 volts, okay? And I mean, if you go here, you will see that we are seeing the particles maybe a little bit better. Okay? So now, I mean, this is my image here. And then you get your topography image when it's done. So let's say around this value, I am in safe side, and it's fine. And then the PI is let's say, PI gain is not too much critical, because they are very small particles. Okay? And then maybe I can scan faster, go again, and let's say, when I can make it up again, then it will start again from here. I mean, you see now, this is a line, but here is like stable, constant line. And then you have see small particles here, you see. And then maybe here we see less. You will see, if you compare now, we see maybe less, a little bit less. So here you have like this peak here, and this it should not go to 0. I mean, here are about 500, and 0 is still half volt. Then it's fine. Okay? So then this is the topography image. And after that, let's say you can make a zoom. If you say, okay, I want to see these particles here, then you just click here, zoom. You select the area you want, let's say here, and you can zoom this area, double click, and you zoom on this area. And then it starts again, scanning this area. I mean, I can clear here, clear all data, so that you will clear the old images, and now it starts again scanning. Okay? So now let's say I have image of 4 micron, and you can start see, okay, this is a particle here, 1, very small one, maybe it's like 5 nanometer, 6 nanometer height. And this line is, let's say, constant, almost. Yes, of course you can show 3D images. Hmm? A new? Yes, you can add a new Windows. Yeah. I mean, here just you click. I mean, right click. Let's say, I mean, there is some Windows here, and then you can make new chart. I mean, there is what is it here? I mean, auto. No, I mean you had. I mean, yeah. Usually you can add. Let's say, right click somewhere and then click a new chart. You can add a new chart and you can put as much as you want. Okay. So, and now you see this is the particles now, okay? If I make here, I can change the color. In just color, yeah, I change the contrast a little bit to maybe see better. I mean, now we start to see some particles now coming, you see? So, and when you look to this line, the most important that this line doesn't go to 0. That's the most important. Do not destroy my tip. And then you see this is, let's say, the particles. I'll put here 45. We can make it shorter. Okay. And then this is my particles here. And once this image is done, then we can make some data processing. Yes, a little bit more parameters to adjust, yeah. Yes, there is a strategy. Yeah, I mean, I mentioned it in my presentation. I said, let's say here you have the free vibration amplitude. This I said, if we have big structure, we increase the vibration amplitude, okay? If we have small structure, we reduce the vibration amplitude. I mean, if you look now, I start as default 200, 2 volt, okay? And then if you look, and then I make image, and then I was seeing that my particles has like 10, 20 nanometer height. And if you, let's say, you can think in your mind that 2 volt is, let's say, 200 nanometer. And I want to see something is like 10 nanometer. So that means I am making very high oscillation. Okay? Then what I do, I reduce my vibration from 2, let's say, to 1. Okay? And then to be sure that my tip is not touching the surface or destroying the surface, I look to the amplitude. You know, here's the amplitude, the second one. And when I am above a particle, you see there is some peaks. And if this peak doesn't go to 0, that means I am following the surface. Clear? Okay? This is the first thing. Then the other parameter to adjust is the set point. And this set point is depending on the material. Usually, if you have hard material, you can start, like, say, with 60%. And when you have, like, say, soft material, you go up to 80%, 90%. Okay? I mean, let's say here we have gold nanoparticles. I mean, they are okay. So, I mean, it's not soft, it's not very hard, it's something okay. So you can start like with 70% or 65%. I mean, most often you start like this parameter. And if you, let's say, work on polymer, sometimes you may increase this to 80%. If you work with DNA or cells, maybe you go to 90%, 95%.
But as a start, 60 maybe...
It's okay. It's a good parameter, as default parameter. We can start with 60. And actually, if there is interaction between tip and material, you will see this line you saw before. You will start to see these lines. I mean, when you are scanning, you will see this line. So it means that the tip has made some interaction with the surface. Okay? Once we get the image, we can do maybe some, let's say, data analysis if you want to show you something. And I mean after 4 o'clock, I will just give you some more idea about really how to measure. Okay. So now we wait, let's say, until the image is finished. Here is saying, let's say, I need 1 minute, 6 seconds to finish my image. And when the image is finished, we can make, let's say, analysis. Let's say you can make it in 3D or roughness analysis or other things. So I can show you. And so you see here that this is the peak here, and then it's not going to 0. That's fine. And then here, these two lines, they are very close to each other, and that's also fine. Okay? And then there is not too much noise, so that's okay. Okay, so the image is done, and then I go to gallery here. So there is gallery. Here I have gallery. I open, and then I open the image. Okay? Then I have the image here. I go to analysis. I can make, let's say, 3D, for example, if you want to see it in 3D. And then you can see the particles here. Maybe I make it bigger. And then maybe I can increase here. And now, and now you can see the particles on the surface. Okay? For example. Then if you say, okay, this is my particles, I want to analyze them. Let's say I want to analyze the size of the particles. Basic analysis here. Okay, you have this is my particles. And then you say, okay, I want to analyze these particles. I make first, let's say I create a cross section, and then I can cut, let's say, these particles with this one, for example. Okay? Double click, then I have this 2 line here. Then I can measure, let's say, the height of these particles. I click here, measure distance, measure from here to here, and this is give us, for example, it's about, let's say, 60 nanometer height. Okay? I can measure also, let's say, this from here to here, and this is give like 60, 67 nanometer height. Okay? Another things you can measure, let's say, if you want to measure the roughness of the surface, you can make here, calculate area roughness. And here is give you, let's say, this is the arithmetic roughness, and this is the root mean square roughness. And this is give you, let's say, the average roughness of the surface is about 6.7 nanometer, which is, let's say, the most important. Usually, when you deposit something, you want to measure roughness, they use always, this, let's say, in literature, they use this value of roughness. Okay? For example. This one.
On the left image, lines.
Here. This is just fitting. Let's say if I go to raw data, they disappear. And because this is, I'm making like line by line fitting. And usually when you make like some fitting, because this is higher than this one, then the software does not correct it properly. So what we need to do, we need to use another software to isolate these particles and make the analysis.
A 3D cross-section can be made.
This is 3D. Okay. Not work. Is it clear? Okay. So what I will do now, I will show you the phase contrast. I mean, the phase contrast is exactly the same things, but what we will do, we'll see how the phase is shifted. Okay. So we will not change anything. We are using always dynamic mode to get the phase contrast images. Okay. So just briefly to explain you fast what we will do. So, I mean, in phase contrast, so what we will do now, I mean, we said we're measuring the excitation amplitude. Now we are just measuring the amplitude on the detector, and we're trying to keep this amplitude constant. Now what we want to do now, we will compare the excitation with the detection, the phase, okay? So if we have here, let's say, now the free vibration amplitude, we have the amplitude, which we are measuring in dynamic mode, and we have also the phase, okay? Then what we will do now, we are closing to the surface. When we are touching the surface, we have different amplitude and different phase, okay? And what we do, usually, we just make comparison between this amplitude, free vibration amplitude, and when we are, let's say, touching the surface, between the excitation and the detector, okay? And then it gives us different amplitude and different phase. I mean, we will interest just in the phase. And phase shift here, okay? So let's say, if we have, let's say here, material on the surface, we have two material, okay? Now when we touch the surface, let's say we have, let's say, less dissipation, let's say, in material. And this make, let's say, small shift. If you have another material which is, let's say, softer, maybe the tip can penetrate more, let's say, in the material. And that would make, let's say, what we'll do like this, it will do big shift on the material, okay, when you are scanning the surface. And in the amplitude, you will see, let's say, you have the one is the initial one, the red one, the blue one, and then when you have, let's say, lower shift or higher shift on the phase images, okay? And this is, let's say, an example here of potassium, let's say, on titanium dioxide. This is the topography image, and this is the phase shift image, where you see here we have, let's say, 3 contrasts. This is the potassium nanoparticles, this is the substrate, and this is, let's say, the solution we deposit on the surface. Because usually we put them in solution, liquid solution, okay?